Hello there, and welcome to Science for Sleep, where curiosity slows down, questions stretch their legs, and science is allowed to wander gently without needing to arrive anywhere too quickly. Tonight, I'd like to invite you on a quiet thought experiment, one that doesn't demand answers right away, only a little attention and a willingness to drift. It's about distance, time, and the simple human habit of looking up and wondering how far we could really go. Space has a way of doing that. Even when we're indoors, even when it's late, even when the lights are low and the world outside feels still, the idea of space presses softly on the mind. Endless, dark, calm, and vast in a way that doesn't rush you. Just the word itself carries a sense of openness, space, a pause, a breath. Somewhere beyond the noise of daily schedules and small obligations, there's a universe moving at its own pace, mostly unconcerned with our calendars. Tonight's question is a deceptively simple one. How far could humans actually travel through space in a single lifetime? Not in the sense of heroic montages or movie trailers, not with triumphant music swelling in the background, but realistically, gently. With biology, physics, time and human limits all taken seriously. No shortcuts, no magic switches, just what the universe allows and what a human body and mind might endure. Before we begin easing into that, let me ask you something quietly. Where are you listening from right now? Are you somewhere familiar or somewhere new? And what time is it there, in your part of the world as these words drift toward you? It's a fitting thing to ask, considering we're about to talk about distance measured not just in kilometres or light years, but in years lived, hours slept, moments noticed. If you find this kind of exploration soothing, or if it helps your thoughts loosen their grip a little after a long day, you're always welcome to like the video or subscribe. It helps this small pocket of calm find others who might need it too. But for now, there's nowhere to click, nowhere to go. Just settle in. Let your breathing slow naturally, without instruction. We're not in a hurry. When people imagine travelling through space, they often picture speed first. Rockets blazing, engines roaring, stars stretching into bright lines. But human travel through space isn't really about speed. It's about time. Time spent accelerating, time spent coasting, time spent waiting, time passing inside a body that still needs sleep, food, warmth and gravity, or at least something close enough to pretend. A human lifetime, after all, is not infinitely flexible. Even under ideal conditions, most of us have a few decades of active years. More if medicine cooperates, fewer if circumstances don't. Space doesn't care about any of that. Distances between planets are large in ways that resist intuition. Distances between stars make even those look modest. And distances between galaxies are so extreme they stop feeling like distances at all, and start feeling like ideas. Still, humans have already travelled farther than our ancestors could have imagined, without ever leaving the surface of Earth. Not physically, perhaps, but perceptually. Telescopes have allowed us to see light that began its journey before our species existed. Probes have carried our presence, in a symbolic sense, to the edges of the solar system. Radio signals, thin and quiet, have spilled outward in expanding spheres, announcing our existence to no one in particular. But tonight isn't about probes or signals, it's about people, flesh, bone, thought, memory. A human stepping onto a vehicle, closing a hatch, and committing a lifetime to motion through darkness. To understand how far that person could go, we first need to be honest about what a lifetime means when removed from Earth. On this planet, time is organised around cycles, day and night, seasons, social milestones. In space, especially deep space, those cycles vanish. There is no sunrise unless you create one artificially, no horizon unless you define it. The passage of time becomes something internal, measured by heartbeats, meals, muscle loss, and the slow shifting of the mind. Even today, astronauts aboard space stations experience time differently. They circle Earth every 90 minutes, watching the sun rise and set multiple times in what feels like a single afternoon. Their bodies struggle to adapt. Bones thin, muscles weaken, sleep becomes fragmented, and these are missions measured in months, sometimes a year. A lifetime is something else entirely. Then there's the issue of distance itself. Space does not scale politely. The moon, which feels far in human terms, is close by cosmic standards. Mars, often described as our next-door neighbour, sits tens of millions of kilometres away at its nearest approach. Even travelling there requires months, careful planning, and acceptance of isolation that few humans have experienced. Beyond Mars, distances grow faster than our imaginations. The outer planets are not just farther away, they are separated by vast regions of emptiness where nothing happens quickly. A spacecraft coasts for years, sometimes decades, with very little change in scenery. No landmarks, no sense of arrival, only gradual confirmation that something distant is becoming slightly less distant. And yet, humans are stubborn. We ask these questions not because the answers are convenient, but because they reveal something about us. We want to know our limits. We want to know whether they are fixed, flexible, or quietly negotiable. One way to think about space travel is to reverse the question. Instead of asking how far a human could go, ask how far space allows a human to remain human. At what point does the distance become less about kilometres and more about survival? At what point does travel turn into something more like endurance? Consider propulsion. Every spacecraft we've built so far relies on throwing mass backward to move forward. Chemical rockets are powerful but inefficient. They burn quickly, accelerate for minutes, and then coast. Once the fuel is gone, speed becomes a constant companion. There is no braking unless you planned for it long ago. That means most space journeys are spent drifting, not soaring, not racing, just moving silently through vacuum at a steady pace. From the inside, it would feel less like travel and more like waiting, interrupted occasionally by course corrections and system checks. Now imagine that waiting stretched across years, then decades, then most of a human life. At some point, distance stops being measured by where you are and starts being measured by what you've left behind. Earth would shrink, not just physically but psychologically. Messages would take longer to arrive. Conversations would turn into delayed exchanges. Familiar voices would age faster than yours, or perhaps slower, depending on the physics involved. Even before we reach questions of near-light speed or distant stars, we have to acknowledge that the nearest meaningful destinations already challenge the boundaries of a single human lifetime. A round trip to Mars, with time spent waiting for planetary alignments, already consumes years. Missions beyond that begin to approach timelines that don't fit neatly into one person's story. This is where the idea of a lifetime in space becomes less about adventure and more about commitment. A choice not just to go somewhere, but to accept that some places cannot be returned from within the span of one life. Travel in this sense becomes directional, not just in space, but in time. And that's before we account for the body itself. Human biology evolved under gravity, radiation shielding, and a thick atmosphere. Space offers none of these by default. Radiation seeps in from all directions. Microgravity quietly reshapes the body. The immune system changes. Vision can blur. The brain adapts in ways we're still learning to understand. A lifetime spent away from Earth would not be a static thing. It would be a continuous negotiation between environment and organism, between intention and adaptation. Still, the question persists. How far could we actually go if we accepted all of that? If we were willing to spend a life in transit, not rushing, not expecting arrival to feel like a finish line? The answer depends on more than technology. It depends on how we define travel. Is reaching a destination necessary, or is movement itself enough? Is a lifetime measured by years lived, or by experiences accumulated? As we move forward, we'll begin placing markers along this path. Not milestones in the traditional sense, but reference points. The Moon, Mars, the outer planets. The edge of the solar system. Each one representing not just distance, but a different relationship between time, motion, and human endurance. And beyond those, stranger possibilities emerge. The bending of time itself. The idea that moving fast enough could stretch a lifetime, allowing one person to cross distances that would otherwise require many generations. Concepts that sound like fiction until physics quietly admits they might not be. But none of that needs to be resolved yet. For now, it's enough to sit with the question, to let it expand gently, without pressure. A human lifetime, a vast universe, and a path between them that is neither short nor simple, but undeniably fascinating. When we talk about a human lifetime in space, it's tempting to imagine a number first. 70 years. 80, if we're optimistic. Maybe more, if medicine continues its slow, determined progress. On Earth, we often reduce a lifetime to a span between two dates, a beginning and an end, neatly printed on documents and headstones. But the moment we lift that idea off the planet and place it into space, it starts to behave differently. A lifetime stops being just a count of years and turns into something shaped by conditions, limitations, and rhythms that are very unlike the ones we're used to. On Earth, a lifetime unfolds within a carefully padded environment. Gravity holds us down without asking. Air presses gently against our skin. Radiation is filtered by atmosphere and magnetism. Day and night follow a predictable cadence, even if we choose to ignore it sometimes. Our bodies are built for this setting, fine-tuned by millions of years of trial and error. Every system inside us assumes this background as a given. When that background disappears, the idea of a lifetime becomes less stable. In space, time still passes at 1 second per second, at least from the perspective of everyday experience. But how that time is filled changes dramatically. A year spent on Earth includes seasons, weather, social interaction, variety of movement, and constant sensory input. A year spent in space, especially far from Earth, would be quieter, more repetitive, and far more constrained. The same number of days might pass, but their texture would be completely different. So when we ask what a human lifetime means in space, we're not just asking how long someone could remain alive. We're asking how long someone could remain functional, how long they could remain psychologically stable, how long they could retain a sense of self that still feels recognizably human. Consider age. On Earth, age is partly biological and partly cultural. A 40-year-old is not just someone whose cells have divided a certain number of times, but someone who has lived through particular experiences, social roles, and expectations. In space, many of those markers fall away. There are no cities to move through, no casual encounters with strangers, no physical communities beyond the people who launched with you. Aging becomes something internal and gradual, less visible, but no less real. Then there is the question of usefulness. On Earth, even as bodies slow down, people can continue contributing in countless ways, teaching, advising, creating, caring. In space, especially on a long-duration mission, usefulness might be tightly coupled to physical capability and cognitive sharpness. A lifetime in space may not offer the same graceful transitions between stages of life that we take for granted here. This raises an uncomfortable but necessary point. A human lifetime in space would likely be shorter in practice than a human lifetime on Earth, not because time itself moves faster, but because the environment accelerates wear. Bone density loss, muscle atrophy, radiation exposure, and changes to cardiovascular and immune systems all place steady pressure on the body. Even with countermeasures, exercise routines and shielding, these effects accumulate. Radiation alone is a defining factor. On Earth, we are bathed in a background level of radiation that our bodies have adapted to. In space, especially beyond Earth's magnetic field, radiation comes from the sun, from distant supernovae, from high-energy particles moving through the galaxy at incredible speeds. This radiation damages DNA, increases cancer risk, and strains repair mechanisms that evolved under gentler conditions. A lifetime in space might not be limited by distance at all, but by how much invisible damage a body can absorb before systems begin to fail. But a lifetime is not only biological, it's also psychological. Humans are not built for isolation on cosmic scales. Even people who enjoy solitude usually rely on the knowledge that connection is available if needed. In deep space, connection becomes delayed, filtered, and abstract. A conversation with Earth could take minutes, then hours, then days, depending on distance. Emotional support arrives long after the moment that needed it. Over time, this changes how the mind experiences life. Memory begins to dominate over immediacy. The past becomes vivid and heavy. The future becomes distant and uncertain. The present, especially in a confined and unchanging environment, can feel suspended. This is not necessarily dramatic or distressing in obvious ways, but it reshapes motivation, attention, and mood. Sleep also behaves differently. Without a natural day-night cycle, the brain struggles to anchor its rhythms. Artificial lighting can help, schedules can be enforced, but the body never fully forgets that something fundamental is missing. Over years, subtle disruptions compound. Fatigue becomes more than just tiredness. It becomes a background condition. So when we talk about a lifetime in space, we're really talking about a balance between survival and experience, between endurance and meaning. A person could technically remain alive for many years under controlled conditions, but whether that time feels like a life, rather than a prolonged holding pattern, is another question entirely. There is also the matter of risk. On Earth, risk is distributed. Accidents happen, illnesses arise, but help is usually nearby. Redundancy exists at a societal level. In space, especially far from Earth, risk concentrates. A single failure can cascade. A micrometeorite puncture, a system's malfunction, a medical emergency with no hospital to divert to. Over a lifetime, the probability of something going wrong approaches certainty. This doesn't mean space travel is impossible. It means that a lifetime in space would not resemble a lifetime on Earth stretched outward. It would be a different kind of existence altogether, shorter in some ways, narrower in others, intense, focused, and shaped by constraints that never fully relax. Now consider time perception. On Earth, we often feel that time speeds up as we age. Years seem shorter, routines blur together. In space, that effect could be amplified. With fewer external changes to mark time, days may merge. Weeks pass quietly. Years might feel both long and strangely thin, filled with repetition rather than novelty. This matters because novelty is one of the ways humans measure life. New places, new faces, new experiences act like bookmarks in memory. Without them, time collapses in hindsight. A decade may feel like it's slipped by without leaving much behind. A lifetime in space could feel shorter, not because it is, but because it contains fewer distinguishable moments. That brings us to an important distinction. There is chronological lifetime, and there is lived lifetime. Chronological lifetime is what clocks record. Lived lifetime is what memory retains. Space travel, particularly long-distance travel, challenges the second more than the first. There is also the social dimension. A human lifetime is rarely solitary. It unfolds in relation to others. Family, friends, colleagues, communities. In space, the social circle would be small and fixed. Conflicts could not be escaped by distance. Relationships would have to endure, adapt, or fracture within the same enclosed volume. Over years, this could reshape personality. People might become more inward, more reflective, or more rigid, or in some cases more patient and deliberate. The environment would select for certain traits: flexibility, emotional regulation, tolerance for monotony. These would become survival skills, not just personality preferences. So when we imagine how far a human could travel in a lifetime, we must also ask what kind of human that lifetime would produce. Not everyone who begins the journey would arrive psychologically intact, even if their body remains functional. And arrival itself may not feel like completion, it might feel like interruption. There is another layer to this question, one that often goes unspoken: purpose. On Earth, purpose evolves. People change careers, relationships, priorities. In space, purpose would likely be defined early and held onto tightly. The mission would become the spine around which identity forms. Over decades, that can be stabilizing, but it can also become brittle. If the mission loses meaning, or if its goals become unreachable, the psychological cost could be profound. A lifetime spent moving towards something that can no longer be reached is a heavy thing to carry. All of this suggests that a human lifetime in space is not just a biological interval, but a carefully engineered experience, one that would need to account for mental health as seriously as propulsion or shielding, one that would need variation, stimulation, and a sense of progress, even if physical distance advances slowly. And yet, humans have endured harsh environments before: polar expeditions, submarines, isolated research stations. These offer small glimpses into what long-term confinement does to people. They show us that adaptation is possible, but not effortless. That support systems matter. That structure, meaning and routine can sustain life where comfort cannot. Space magnifies these lessons. It strips away the illusion that a lifetime is simply something that happens. In space, a lifetime would have to be actively maintained. So as we continue forward, when we begin talking about distances and speeds and trajectories, it's worth holding this definition quietly in mind. A human lifetime in space is not just the span between launch and death. It is the sum of physical resilience, psychological endurance, social stability, and purpose, all unfolding in an environment that offers very little forgiveness. How far someone could travel, then, is inseparable from how long they can remain themselves along the way. And that question doesn't have a clean numerical answer. It has conditions, trade-offs, and limits that are less about engines and more about what it means to live a life when almost everything familiar has been left far behind, still moving forward, without needing to arrive just yet. When people start thinking about how far humans could travel through space in a lifetime, attention almost immediately turns to speed. It's a natural instinct. Distance feels conquerable if speed is high enough. On Earth, this intuition works fairly well. Faster planes shrink continents. Faster trains turn day-long journeys into short commutes. Speed, in everyday life, is a kind of permission slip. It allows us to imagine farther destinations without increasing the time they demand from us. Space, however, does not reward this intuition so generously. Out there, speed is not just a convenience, it is a fundamental constraint, one that sits at the heart of how the universe is built. There is a maximum, and it is not negotiable. No matter how advanced the technology, no matter how much energy is available, no object with mass can exceed it. That limit is the speed of light, and it always wins. Light moves at about 300,000 kilometers per second in a vacuum. That number is so large it resists emotional comprehension. Light could circle Earth more than 7 times in a single second. It could travel from the Moon to Earth in a little over a second. Compared to anything humans normally experience, it is absurdly fast. And yet, compared to the size of the universe, it is surprisingly slow. The distance between Earth and the Sun is such that sunlight takes a bit over 8 minutes to arrive. When you look at the Sun, you're not seeing it as it is now, but as it was 8 minutes ago. That delay is already baked into reality. Stretch that outward, and things become stranger. Light from Jupiter takes over half an hour to reach us. Light from the nearest star system, Alpha Centauri, takes more than 4 years. Light from the center of our galaxy takes around 26,000 years. The universe we see is always a little old. This is the first quiet lesson of cosmic speed limits. Distance is not just space, it is time. Every meter traveled requires duration, and no amount of engineering has ever found a way around that. Why does light get this special status? Why is it allowed to move at this speed while everything else is held back? The answer lies deep in the structure of space-time itself. The speed of light is not just the speed of the light. It is the speed at which cause and effect propagate. It is the maximum speed at which information can travel. Change, influence, interaction, all are capped by this value. This means the speed of light is not really about light. It's about reality keeping itself consistent. If information could travel faster than this limit, effects could occur before causes. Events could influence the past. The logical structure of the universe would unravel. The speed limit is less like a rule imposed from outside and more like a property of the universe protecting its own coherence. For humans, this creates an immediate tension. Our lifetimes are short compared to cosmic distances. Even at incredible speeds, the universe remains stubbornly large. Travelling fast enough to make distant stars reachable within one life runs directly into the wall that light erects. Now, it's important to be precise here. Nothing prevents humans from travelling close to the speed of light. Physics allows it in principle, but getting closer requires more and more energy, and the closer you get, the steeper the cost becomes. At low speeds, acceleration feels manageable. At higher speeds, energy demands explode. Approaching the speed of light, the required energy rises toward infinity. You never quite get there. This is not a technical limitation, it's a fundamental one. You cannot simply build a better engine and solve it. No clever materials or futuristic fuels bypass this curve. The universe is very firm on this point. From the perspective of someone standing still relative to you, your ship gets heavier as you speed up. Not metaphorically heavier, relativistically heavier. Your mass resists acceleration more and more. The equations refuse to cooperate. Every additional fraction of speed costs more energy than the last, until the idea of reaching light speed becomes physically meaningless. This has a direct impact on the idea of lifetime travel. If you're limited to speeds far below light speed, distances remain brutally large. The nearest stars take tens of thousands of years to reach using propulsion systems we can realistically imagine today. Even optimistic future technologies still struggle to bring that down to timescales compatible with a single human life. But relativity adds a twist, one that complicates the picture in a subtle and often misunderstood way. Time itself behaves differently at high speeds. If you travel fast enough, time passes more slowly for you relative to someone who remains behind. This is not a perception trick, it is measurable and real. Clocks aboard fast-moving spacecraft tick more slowly than clocks at rest. This effect, known as time dilation, opens a narrow conceptual door. While the universe still refuses to let you exceed the speed of light, it does allow you to experience less time while travelling at very high speeds. From your perspective, the journey takes fewer years. From the perspective of those you left behind, much more time passes. In theory, this means a human could traverse distances that would normally require many lifetimes, as long as they are willing to accept that everyone they knew on Earth would age far more quickly, possibly disappearing entirely before they ever arrive. However, this does not defeat the speed limit. It bends time, not space. The distance remains what it is. The universe still enforces causality. Light still arrives first, and the practical problems remain enormous. Accelerating a human-sized spacecraft to a significant fraction of light speed requires energy on a scale that borders on the astronomical. It would demand power sources far beyond anything we currently possess, and shielding capable of surviving impacts with even microscopic particles at relativistic speeds. At those velocities, a grain of dust becomes a bullet with the energy of an explosion. Even empty space is not truly empty. There are stray atoms, photons, cosmic rays. At near-light speeds, collisions with these become lethal threats. The faster you go, the more violent the universe becomes. This is another way light always wins. Not only does it set the limit, it defines the environment. At high speeds, space itself turns hostile in ways that are difficult to fully mitigate. So when imagining human travel, speed becomes a double-edged concept. Faster travel shortens subjective time, but it dramatically increases engineering complexity, energy demand, and risk. Slower travel is safer in some respects, but condemns the journey to durations far beyond a single lifespan. Between these extremes lies a narrow corridor of possibility. Speeds fast enough to meaningfully reduce travel times within a lifetime, but slow enough to remain survivable and achievable. That corridor is uncomfortably narrow. It also forces us to rethink what we mean by distance. On Earth, distance is something you cross. In space, distance is something you endure. Light makes this distinction unavoidable. It moves effortlessly at its maximum speed, but it cannot go faster. Everything else must accept second place. There is something quietly humbling about this. Light is massless. It does not age. It does not tire. It does not require food, protection, or rest. It moves because that is what it is. Humans, by contrast, are heavy with needs. We carry biology with us. We cannot outrun it. The universe seems structured in a way that favours signals over travellers. Information spreads freely, but bodies lag behind. We can see far more than we can go. We can know about distant galaxies, map their motions, analyse their chemistry, all while remaining physically bound to a small region of space. This asymmetry shapes the future of exploration. It suggests that most of humanity's relationship with the cosmos will be observational rather than migratory. Probes and light will always go farther than people. Yet the question of lifetime travel persists because humans do not experience life as equations. We experience it as narrative, and narratives care deeply about journeys. If a human spends 30 years accelerating, 20 years coasting, and 30 years decelerating, arriving somewhere distant at the end of a long life, does that count as reaching far? Or does the universe measure distance differently, indifferent to how it felt along the way? Light doesn't ask these questions, it simply moves. But humans do ask them, because our limits force reflection. The speed limit of the universe is not just a technical barrier, it is a philosophical one. It tells us that there are places we can know but not touch, distances we can measure but not cross, futures we can imagine but not inhabit. And yet within that limit there is still room to move, still room to stretch a lifetime in strange ways, still room to trade shared time for distance, or distance for time. Before anyone ever strapped themselves into a capsule or watched a countdown reach zero, humans had already travelled astonishing distances through space without moving an inch from Earth's surface. This idea sounds paradoxical at first, but it becomes clearer the moment you remember that Earth itself is never still. We live on a planet that spins, orbits, drifts, and participates in motions so vast that even a quiet night's sleep carries us farther than the most ambitious ancient journey ever could. Start with the most immediate motion, the rotation of Earth. At the equator, the surface of the planet moves at roughly 1,070 kilometers per hour. You don't feel this because everything around you is moving at the same speed. Your body, the air, the buildings, the oceans all share the motion. But the distance adds up. If you're standing near the equator and simply remain there for 24 hours, you will have travelled more than 40,000 kilometers through space, carried along by Earth's spin alone. Even at higher latitudes, where the rotational speed is lower, the distance remains enormous on a human scale. Now add Earth's orbit around the Sun. Our planet traces a vast, nearly circular path through space once every year, moving at about 107,000 kilometers per hour. That means that over the course of a single day, Earth carries you roughly 2.6 million kilometers along its orbit. Over a year, that becomes about 940 million kilometers, nearly 1 billion kilometers travelled without ever feeling acceleration, wind, or resistance. Already the numbers begin to stretch intuition. A person who has lived 30 years on Earth has, by default, travelled nearly 28 billion kilometres around the Sun. Someone who has reached the age of 80 has been carried along for more than 75 billion kilometres. These are distances that dwarf the journeys of early spacecraft, and they are accumulated simply by existing. But Earth's motion does not stop there. The Sun itself is not stationary. It orbits the centre of the Milky Way galaxy, dragging the entire solar system along with it. This motion is slower to grasp emotionally, because it unfolds over hundreds of millions of years, but the speed involved is still immense. The Sun moves at roughly 828,000 kilometers per hour as it circles the galactic centre. When you combine this with Earth's daily and yearly motions, the picture becomes layered. You're rotating, orbiting, and galactically drifting all at once. Each motion stacks on top of the others. Over the course of a single day, your body traces a complex spiralling path through space that would be almost impossible to draw accurately. Extend this over a human lifetime, and the distances become staggering. In 80 years, you have travelled tens of billions of kilometres around the Sun and hundreds of billions of kilometres through the galaxy, all without leaving your bedroom. This reframes the idea of travel in a subtle but important way. Humans often think of travel as something intentional, something that requires effort, fuel, and planning. But in cosmic terms, motion is the default. Stillness is the illusion. The universe moves you whether you consent or not. There is another layer to this invisible journey, one that involves not just physical displacement, but observation. Humans have extended their reach through space by learning how to see farther rather than go farther. Telescopes are, in a sense, vehicles for the mind. When you look at a distant object through a telescope, you're not only seeing across space, you are seeing back in time. Light takes time to travel. This simple fact turns observation into a kind of journey. When you look at the moon, you are seeing it as it was just over a second ago. When you look at the Sun, you are seeing it as it was 8 minutes ago. When you look at the nearest stars, you're seeing years into the past. When you look at distant galaxies, you're seeing events that happened millions or even billions of years ago. In this way, humans have already extended their experience across vast stretches of space-time. Astronomers routinely work with data that originated long before Earth had complex life. The oldest light we can observe comes from the early universe itself, dating back to a time when the cosmos was only a few 100,000 years old. No spacecraft has travelled that far, but human perception has. This matters because it highlights a different kind of distance. Physical distance limits where bodies can go. Observational distance determines how far understanding can reach. In terms of knowledge, humans have already crossed the observable universe, even though no physical object we've built ever will. There is also the quiet but powerful distance travelled through communication. Radio waves move at the speed of light, spilling outward from Earth in an expanding sphere. Every broadcast, every radar pulse, every television signal from the early days of radio has continued moving outward, thinning as it goes, but still travelling. These signals now extend more than 100 light-years into space. That means that, in a very real sense, fragments of human presence have already reached distant star systems. Not as ships, not as explorers, but as whispers, music, voices, static, patterns, weak and probably undetectable against cosmic noise, but undeniably there. This is another way humans have travelled without leaving Earth. We have allowed our influence, however faint, to move outward at the maximum speed allowed by the universe. Long before any human body could follow, the signature of our existence has already gone ahead. Even our probes, though technically they leave Earth, illustrate a similar principle. They are extensions of human intent rather than human bodies. When a spacecraft like Voyager crosses into interstellar space, it carries no living person, but it carries information, culture, and records of our world. It is a message in motion, a proxy traveller. The distances these probes cover are impressive by engineering standards, but modest by cosmic ones. Voyager 1, after more than 4 decades of travel, is about 24 billion kilometres from Earth. That sounds enormous until you realise it's still less than a light day away. Light crosses that distance in under 24 hours. This contrast helps calibrate expectations. A human lifetime feels long because it contains memories, changes, and meaning. In terms of distance at cosmic speeds, it is brief. Earth carries us far, but not far enough to bridge the gulfs between stars. There is also a psychological component to this invisible travel. Knowing that you're constantly moving through space changes how distance feels. The universe is not something you occasionally enter by launching upward. It is something you are already immersed in. Earth is not a base camp outside the cosmos. It is a vehicle within it. This perspective softens the boundary between staying and going. When people imagine space travel, they often picture a sharp transition. Earth below, space above. But the truth is more continuous. The atmosphere thins gradually. Gravity weakens gradually. Motion never stops. In that sense, humans have never truly been confined to Earth. We have been carried through space since the planet formed. Our entire evolutionary history unfolded aboard a moving world. That does not mean physical travel is unimportant. Leaving Earth introduces new challenges, new risks, new possibilities, but it does mean that distance itself is not foreign to us. We are already travellers on a scale that defies everyday intuition. This matters when thinking about how far we could go in a lifetime. The question is not starting from zero. It is starting from a baseline of constant motion. The universe has already done much of the work. Another way humans have travelled without leaving Earth is through mathematics. Equations allow us to explore conditions we cannot physically reach. The interior of stars, the edge of black holes, the earliest moments after the beginning of the universe. These are environments no human body could survive, yet they are familiar territory to theoretical models. Mathematics is a form of travel without displacement. It allows the mind to inhabit scenarios far removed from sensory experience. In terms of understanding, this has taken us farther than any rocket ever could. This intellectual travel feeds back into physical limits. By understanding the structure of space-time, the behaviour of energy, and the constraints imposed by physics, humans have learned not just where they might go, but where they cannot. Knowing the limits is itself a kind of journey. All of this reframes the central question. How far could humans actually travel through space in a lifetime is not only about engines and destinations, it is also about recognizing that a lifetime already contains vast motion, vast reach, and vast exposure to the universe. A person who never leaves Earth still experiences the cosmos in deep ways. They are carried through it, informed by it, shaped by its rhythms. Their atoms were forged in stars long before the planet existed. Their body is a temporary arrangement of cosmic material, passing through space aboard a moving world. This perspective does not diminish the desire to go farther. If anything, it grounds it. It reminds us that travel is not an all-or-nothing proposition. There are degrees of distance, degrees of presence, degrees of participation. The question becomes one of increment rather than initiation. How much farther can we push beyond the distances already granted to us by the universe itself? How much more motion can a human life meaningfully contain? When people think about human space travel in concrete terms, their minds often settle on the moon. Not because it is the farthest place we've reached, but because it is the farthest place humans have ever stood. That distinction matters. The moon is close enough to feel attainable, yet distant enough to feel otherworldly. It sits in a strange middle ground between Earth and the rest of the universe, and that is precisely why it continues to matter so much when we talk about how far humans can go in a lifetime. The distance to the moon is about 384,000 kilometers. On a cosmic scale, that number is almost insignificant. Light crosses it in just over a second. Compared to the distances between planets, let alone stars, it barely registers. And yet, for a human body, for a human mind, for a human society, it represents a profound step outward. It is far enough that Earth no longer dominates your entire field of view. Far enough that the planet becomes an object rather than an environment. Far enough that return is no longer automatic. Reaching the moon was not just a matter of speed or fuel. It was a matter of precision, planning, and trust. in systems that had never been tested under those exact conditions before. The Apollo astronauts were not merely travelling through space, they were temporarily stepping outside the protective envelope that has sheltered life on Earth for billions of years. No thick atmosphere, no global magnetic field, no immediate rescue if something went wrong, and yet the journey itself was relatively brief. From launch to lunar orbit took about 3 days. 3 days to cross a distance that feels enormous from the ground, but passes quietly when measured against a human lifespan. This is important to notice. The Moon is one of the few places beyond Earth that fits comfortably within the time budget of a human life, without requiring extreme trade-offs. A person could, in principle, travel to the Moon, work there, return, and still live out the majority of their life on Earth. The journey does not demand decades. It does not sever connection permanently. It does not require that one's entire identity be bound to the act of travel itself. That makes the Moon unique. When the Apollo missions landed, the astronauts did not arrive as conquerors or settlers. They arrived as visitors, temporary ones. They brought with them the necessities of survival and very little else. Their stays were measured in hours and days, not years. Yet those brief visits permanently altered how humanity understood its place in the universe. From the surface of the Moon, Earth hangs in the sky. Small, bright, fragile looking. It does not rise or set in the same way the Moon does when viewed from Earth. It hovers, almost still, a blue and white sphere suspended in darkness. For the first time, humans could see their entire world at once, not as an abstract concept, but as a single, bounded object. This view changed more than space exploration. It changed environmental awareness. It changed philosophy. It changed the way people talked about borders, resources, and shared responsibility. The Moon did not just extend human reach. It reframed human perspective. That alone would be enough to justify why the Moon still matters. But there is more. The Moon represents a test case for long-term human presence beyond Earth. Not in theory, but in practice. Its distance is great enough to introduce meaningful delay in communication, but small enough that help could, in principle, arrive within days. Its environment is hostile, but not as extreme as deep space or planetary surfaces farther out. Its gravity is weaker, but not absent. This makes the Moon an ideal place to learn what a sustained human presence away from Earth actually requires. Not for a few days, but for months, then years, then perhaps decades. Living on the Moon would challenge nearly every system humans rely on. Life support would need to be closed loop. Air, water, and waste would need to be recycled with high efficiency. Radiation shielding would need to be substantial, likely involving regolith, the fine dusty soil that covers the lunar surface. Power generation would need to contend with long, lunar nights that last about 2 Earth weeks. These are not abstract challenges. They are the same kinds of challenges that would arise on Mars or in deep space habitats. The Moon allows us to face them without committing to journeys that consume a large fraction of a human lifetime just in transit. From the perspective of lifetime travel, this is crucial. Every day spent travelling is a day not spent living at a destination. For farther targets, the balance tips quickly. The Moon keeps that balance manageable. There's also the matter of human adaptation. Extended stays on the Moon would expose people to lower gravity over long periods. Lunar gravity is about 1/6 that of Earth. This is enough to allow walking, working and building, but it places different demands on the body. Bones would bear less load, muscles would work differently, fluids would redistribute. Studying these effects over years rather than weeks would tell us how much gravity humans actually need to remain healthy over a lifetime. This question is still unanswered. We know that zero gravity causes significant degradation. We do not yet know where the lower limit lies. The Moon offers a natural experiment. If humans cannot maintain long-term health at 1/6 gravity, that has implications far beyond the Moon. It would shape expectations for Mars, which has about 1/3 Earth's gravity, and for artificial habitats that rely on rotation to simulate gravity. In this way, reaching the moon is not just about the moon. It is about mapping the boundary conditions of human life. There is also the psychological aspect. Distance affects the mind as much as the body. On the moon, Earth is always visible from the near side. This constant visual connection could be comforting, or it could be unsettling. Seeing home but knowing it is unreachable without complex machinery might produce a unique form of homesickness. At the same time, the moon offers something rare in space travel, a sense of place. The surface is solid, horizons exist, landmarks can be named, footprints remain. This is different from orbital habitats, where up and down are conventions rather than realities. For a human spending a significant portion of their life beyond Earth, this sense of place could matter deeply. It anchors experience, it provides context, it allows memory to attach itself to location. The moon also occupies a strategic position in discussions of how far humans could go. It is often described as a stepping stone, but that phrase can be misleading. Stepping stones imply quick movement onward. In reality, the moon may function more like a training ground, a proving ground, or even a long-term companion to Earth rather than a mere waypoint. From the moon, launching deeper into space requires less energy than launching from Earth. Its weaker gravity makes it easier to send materials outward. In this sense, a human lifetime that includes time spent on the moon could support journeys that would be impractical if everything had to start from Earth's surface. This raises an interesting possibility. Perhaps the farthest humans travel in a lifetime will not be defined by a single uninterrupted journey but by phases. Earth to moon, moon to somewhere else. Each phase occurring within a stable environment that allows rest, recovery and adaptation. If that is the case, the moon becomes less of a destination and more of a rhythm. A place where movement pauses long enough for life to reassert itself. There is also the cultural significance. The moon is woven into human history in ways no other celestial body is. It has marked time through phases, guided navigation, inspired myth, poetry, and science. Seeing it up close did not strip it of meaning, it added layers. Future generations growing up with the idea that humans live and work on the moon would inherit a different sense of normal. Distance would feel different. The idea of leaving Earth would no longer be singular or shocking. It would be part of a continuum. This matters for lifetime travel because ambition is shaped by expectation. What one generation sees as extraordinary, the next may see as routine. A person born into a world where lunar travel is normal may imagine farther journeys as plausible within their own life. At the same time, the moon serves as a reminder of limits. It shows how hard even short distances can be when biology is involved. 6 Apollo missions landed humans on the moon. That was over half a century ago. No one has returned since. The difficulty was not just technical. It was political, economic, and cultural. This highlights an often overlooked aspect of lifetime travel. Capability does not guarantee continuity. Humans may be able to go somewhere, but whether they choose to keep going depends on priorities that shift over time. The moon stands as proof that reaching a place once does not mean it becomes permanently integrated into human life. Distance alone does not determine destiny. Commitment does, and yet interest in the moon persists. Plans are made, delayed, revived, revised. This persistence suggests that the moon occupies a stable position in the human imagination. It is close enough to matter, far enough to challenge, and familiar enough to invite return. When considering how far humans could travel in a lifetime, the moon represents a boundary that has already been crossed, but not fully absorbed. It is a place where the question shifts from can we reach it to how do we live there, and for how long? That shift is subtle, but profound. It marks the transition from exploration as a series of stunts to exploration as a mode of existence. A human lifetime spent partly on Earth and partly on the moon would already be a radically different life than any lived before the space age. It would involve different rhythms, different risks, different definitions of home. And yet, it would still be recognizably human. This makes the Moon a kind of reference point. Not the farthest we could go, but the farthest we have gone while remaining tethered to Earth in a meaningful way. It is the outer edge of the familiar. The Moon reminds us that distance is not just something to overcome, it is something to inhabit. And learning how to do that carefully and deliberately may matter more for how far humans can travel in a lifetime than any single leap outward. Beyond the Moon's familiar grey horizon, space begins to stretch in ways that feel less ceremonial and more consequential. The distances stop being symbolic and start becoming logistical. This is where questions of human reach sharpen, where enthusiasm meets arithmetic, and where a lifetime begins to feel like a finite resource rather than a generous allowance. Mars and the asteroids sit right at that threshold, close enough to imagine, far enough to demand commitment, near human reach but not comfortably so. Mars has long held a special place in the human imagination. It looks like a planet that might almost be Earth, if you squint and forgive it a few billion years of bad luck. It has days nearly the same length as ours, it has seasons, it has polar ice, it even has weather, though the winds are thin and the storms are mostly dust. Compared to the gas giants or the frozen outer worlds, Mars feels approachable, like a place that might meet us halfway. But the distance tells a more complicated story. Mars does not orbit the Sun at a fixed distance from Earth. Sometimes it is relatively close, about 56 million kilometers away. Sometimes it's on the opposite side of the Sun, more than 400 million kilometers distant. These changing positions mean that travel windows are limited. Efficient missions to Mars can only launch during certain alignments that occur roughly every 26 months. When those windows open, the journey itself typically takes between 6 and 9 months using current propulsion methods. That is not a trivial amount of time. It is long enough for the human body to begin changing in noticeable ways due to microgravity. It is long enough for isolation to settle in. It is long enough that the idea of just going there becomes something more serious, and that is only the outbound trip. Once on Mars, immediate return is not usually possible. The same orbital mechanics that allowed departure now dictate waiting. Astronauts would likely need to remain on the surface for well over a year before conditions allow a return journey. Add the return transit, and a single Mars mission quickly approaches 2.5 to 3 years. That length of time fits within a human lifetime, but it consumes a significant portion of an active adult life. It is not something one casually repeats. A person who goes to Mars is not taking a trip. They are making a choice that reshapes the arc of their life. This is why Mars marks a clear edge. It is the first destination beyond Earth where human travel stops being episodic and starts becoming immersive. The timeline alone forces that shift. You cannot dip in and out of Mars the way you might with the Moon. You commit to it. Then there are the environmental realities. Mars has an atmosphere, but it is thin, about 1% of Earth's atmospheric pressure. It offers minimal protection from radiation. Solar and cosmic radiation reach the surface far more easily than they do on Earth. Over months and years, this exposure accumulates. Mars also has gravity, but only about 38% of Earth's. This is more than the Moon, but still far below what human bodies evolved under. We do not yet know whether this is enough to maintain long-term health over decades. It might be. Or it might slowly erode bones, muscles, and cardiovascular function in ways that only become obvious after many years. Living on Mars would therefore be an experiment in slow adaptation. Every system, biological and technological, would be operating outside its comfort zone. A human lifetime spent partly on Mars would be a data set as much as a personal story. Psychologically, Mars presents a different challenge than the Moon. Earth would no longer hang large and bright in the sky. At its closest, Earth would look like a bright star. At its farthest, it would be nearly lost among others. Communication delays would range from about 4 minutes to over 20 minutes one way. Conversations would become exchanges of messages, not dialogues. This changes how support works. On the Moon, help is days away. On Mars, help is months away, and only during certain seasons. the concept of rescue begins to lose meaning. Self-sufficiency becomes not just a goal, but a requirement. For a human lifetime, this has implications beyond survival. It affects how people make decisions, how they cope with uncertainty, how they handle mistakes. The margin for error narrows. Stress becomes chronic rather than acute. Over years, that kind of psychological load shapes personality. Yet Mars also offers something the Moon does not. Scale. A sense of a world rather than a site. There are valleys, mountains, plains. There is geological history written into the landscape. There is the possibility, however remote, that life once existed there. For humans, this matters. We respond differently to environments that feel expansive. A lifetime spent on Mars might feel more like living somewhere than merely enduring somewhere. That distinction could be crucial for mental health over long durations. Now shift attention slightly outward, away from planets and toward asteroids. These are often overlooked in popular imagination, but they occupy a fascinating position in discussions of human reach. Asteroids are not destinations in the traditional sense. They are not worlds. They are remnants. Leftover building blocks from the early solar system, scattered in belts and clusters. Some orbit between Mars and Jupiter. Others cross Earth's path. A few wander farther out. From a travel perspective, asteroids present an unusual profile. Some are closer than Mars at certain times. Some require less energy to reach than landing on a planetary surface because they have extremely low gravity. You can approach them, match velocity, and effectively dock without needing to land in the conventional sense. This makes asteroids attractive targets for exploration and resource utilization. Water, metals, and other materials could, in theory, be extracted and used to support further space activity. But for human travellers, asteroids also pose unique challenges. There is no surface in the way we usually understand it. Gravity is so weak that walking is impossible. Movement becomes a careful dance of pushing and pulling. Orientation loses meaning. Up and down dissolve. For a human spending significant time near an asteroid, this could be deeply disorienting. The inner ear relies on gravity to provide cues about balance and orientation. Without it, even trained astronauts experience confusion and nausea. Over months or years, the brain adapts, but the experience remains fundamentally alien. Asteroids also offer no natural protection from radiation. Any long-term human presence would require substantial artificial shielding, likely built from the asteroid's own material. This is technically plausible, but complex. From a lifetime perspective, asteroids sit in an odd position. They are reachable within a human life. Some could be reached and returned from within a few years. Others could serve as semi-permanent outposts, but they do not offer the psychological grounding that planets do. A human lifetime spent near asteroids would likely be a lifetime spent in transit rather than residence. A series of operations, relocations, adjustments. It would feel more like working at sea than settling on land, except the sea is replaced by vacuum. Mars and asteroids together define the outer boundary of what we might reasonably call near human reach. Beyond them, travel times stretch dramatically. The outer planets are years away, even with fast trajectories. Jupiter alone is 5 times farther from the Sun than Earth. Saturn is nearly 10 times farther. Missions to these regions are measured in decades for robotic probes. For humans, the timelines quickly exceed what feels compatible with a single life, at least as we currently understand it. Even reaching Jupiter would require many years of travel one way, followed by a harsh radiation environment that challenges survival. This is where the concept of lifetime becomes less about years lived and more about years available. A person who spends 15 years travelling outward and 15 years travelling back has spent half a career in transit alone. Add time at destinations, training, recovery, and the margins shrink. Mars represents the last place where travel and living might reasonably coexist within one life without requiring extreme measures. Asteroids represent the last places where humans might work rather than live, still within reach of Earth in a broad sense. Everything beyond begins to demand either generational thinking or relativistic effects that change how time itself is experienced. This is why Mars continues to matter so much. It is not just another planet. It is the place where the question shifts from can we get there to can we afford to spend our lives doing this? A person who goes to Mars is not just travelling through space. They are choosing to allocate years of their finite existence to distance. That choice has weight. The same is true, in a different way, for asteroids. Time spent near them is time spent away from any stable notion of home. It is time lived in environments that never let you forget how artificial your presence is. And yet, humans have always pushed toward edges like this. Edges where comfort fades but possibility expands. The history of exploration is filled with people who accepted long separations, uncertain returns, and lives shaped by motion rather than stability. What changes in space is that the scale becomes unforgiving. Mistakes are not easily corrected. Time cannot be reclaimed. Distance amplifies every decision. So when we talk about Mars, asteroids, and the edge of near-human reach, we are really talking about the last places where a human life can stretch outward without breaking entirely from Earth's influence. They're close enough that Earth still matters, far enough that Earth no longer defines everything. Mars and the asteroids stand as markers, not endpoints, but thresholds. Places where a human can still go, still work, still live portions of a life, while standing at the brink of distances. Long before distance becomes the deciding factor in how far humans can travel through space, the body quietly steps forward and asks to be considered. Not loudly, not all at once, but gradually, through small changes that accumulate over time. A few weeks away from Earth already produces measurable effects. A few months reshape muscle and bone. Decades would do something far more fundamental. They would redefine what a human body becomes when removed from the conditions that shaped it. On Earth, the body is constantly negotiating with gravity. Every movement, even standing still, requires muscles to engage and bones to bear weight. The heart works against gravity to push blood upward. Fluids settle downward. The inner ear uses gravity as a reference point to orient balance and motion. These processes happen so automatically that we rarely notice them. They form the background assumptions of human physiology. Space removes that background. In microgravity, the body is suddenly freed from loads it evolved to expect. At first, this feels like relief. Astronauts often describe the sensation as floating effortlessly, as if weight has been lifted not just from the body but from the mind. Movements require little effort. Objects stay where you leave them. The spine elongates slightly as it decompresses, often making astronauts a bit taller for a time, but this apparent ease is deceptive. The body interprets the lack of load as a signal that certain systems are no longer needed at full capacity. Muscles that are not required begin to weaken. Bones that are not stressed begin to lose density. The body is efficient, sometimes too efficient. It conserves resources by dismantling structures it believes are unnecessary. Over weeks, muscle atrophy becomes noticeable. The muscles most affected are those involved in posture and movement against gravity on Earth, especially in the legs and back. Even with daily exercise routines designed to simulate load, these muscles still weaken. Exercise in space helps, but it does not perfectly replicate the complex stresses of gravity-driven movement. Bones follow a similar pattern. Bone is living tissue, constantly being broken down and rebuilt. On Earth, the stress of weight-bearing activities signals bones to maintain strength. In microgravity, that signal fades. Calcium is released from bones into the bloodstream, reducing bone density. This process resembles accelerated osteoporosis. Over months, the loss is measurable. Over years, it becomes significant. Over decades, it raises serious questions about structural integrity. A body that has spent decades in microgravity might struggle to support itself if returned to Earth-like gravity. Fracture risk would be high. Recovery, if possible at all, would be long and uncertain. The cardiovascular system also changes. Without gravity pulling blood downward, Fluids redistribute toward the upper body and head. Faces become puffier, legs lose volume. The heart, no longer needing to work as hard to pump blood upward, begins to weaken slightly. Blood volume decreases. When astronauts return to Earth, many experience dizziness or fainting when standing up. Their cardiovascular systems must relearn how to manage gravity. Over long durations, this adaptation becomes deeper. A heart conditioned to microgravity may not easily readapt to sustained gravitational load. Then there is the immune system. Studies have shown that spaceflight alters immune function in complex ways. Some aspects become suppressed, others become overactive. Latent viruses that have been dormant in the body for years can reactivate. Inflammation patterns change. Over decades, a persistently altered immune system could increase susceptibility to infection or autoimmune conditions. In a closed environment where microbial populations are limited but persistent, this creates additional challenges. Even minor illnesses could have outsized effects. Radiation exposure compounds all of this. Outside Earth's magnetic field, the body is exposed to higher levels of ionizing radiation from cosmic rays and solar events. This radiation damages DNA. The body can repair some of this damage, but not all of it. Errors accumulate. Over years, the increased cancer risk becomes significant. Over decades, it becomes one of the primary limiting factors for long-term human presence in space. Shielding can reduce exposure, but it cannot eliminate it entirely without impractical amounts of mass. Radiation also affects the nervous system. There is growing evidence that long-term exposure to cosmic radiation may impact cognitive function. Changes in attention, memory, and processing speed have been observed in animal studies. Human data is still limited, but the implications are concerning. A lifetime in space would therefore involve not just physical decline, but potential cognitive drift. Subtle at first, difficult to notice day by day, but meaningful when measured across decades. Vision changes are another documented effect. Some astronauts experience a condition known as spaceflight-associated neuroocular syndrome. Fluid shifts increase pressure inside the skull, flattening the back of the eye and altering vision. For some, these changes persist after returning to Earth. If such effects accumulate over long durations, they could impact daily functioning. Fine motor tasks, reading, operating equipment all depend on stable vision. The digestive system also adapts. Changes in gut microbiota have been observed during spaceflight. Diet is restricted. Food variety is limited. Over years, this could affect nutrient absorption, metabolism, and overall health. Sleep, already challenged by disrupted light cycles and operational demands, becomes a long-term concern. Chronic sleep deprivation or misalignment affects nearly every system in the body. Hormones, mood, cognition, immune function all suffer when sleep is compromised. On Earth, circadian rhythms are reinforced by natural light, social cues, and environmental changes. In space, these cues must be artificially maintained. Over decades, even small misalignments could add up. Then there is reproduction, a topic still largely unexplored in space. Human reproduction has never occurred beyond Earth. We do not fully understand how microgravity and radiation would affect fertility, pregnancy, or fetal development. Animal studies suggest potential complications. For a human lifetime in space that includes multiple generations, this becomes a central issue. But even for an individual lifetime, the inability to reproduce, or the risks associated with it, would shape social dynamics and personal identity. All of these changes point to a deeper truth. The human body is not a static object that can be placed anywhere and expected to function indefinitely. It is a dynamic system tuned to a specific environment. Remove it from that environment, and it begins to retune itself, sometimes in ways that conflict with long-term health. This does not mean humans cannot adapt. We are remarkably flexible organisms. But adaptation often comes with trade-offs. A body optimized for microgravity may not be compatible with gravity. A body shielded from Earth's microbial diversity may respond unpredictably to new exposures. There is also the psychological dimension of bodily change. Living in a body that is slowly, irreversibly changing in response to an alien environment affects how a person experiences themselves. Strength fades, endurance shifts, sensations alter. Over decades, identity may adjust. A person who has lived most of their life in space may not consider these changes losses. They may simply be normal. Earth normal might feel strange to them. This raises an important question. When we talk about what happens to the human body over decades in space, are we talking about damage or transformation? The answer may depend on perspective. From Earth's point of view, many of these changes look like degradation. From the perspective of someone who has adapted to space, they may represent specialization, a body suited to floating, to low-load movement, to confined environments. However, specialization narrows options. A body adapted to space may struggle to return. That return, if attempted, could be more traumatic than the initial departure. This matters for lifetime travel. A person who spends decades in space may be committing not just to distance, but to permanence. The longer the stay, the harder the return. Technology can mitigate some of these effects. Artificial gravity through rotation could provide load. Better shielding could reduce radiation. Medical advances could support immune function and tissue repair. But each solution introduces complexity and cost. Artificial gravity habitats, for example, require large structures and constant maintenance. They are not trivial to build or operate. Radiation shielding adds mass, which complicates propulsion. Medical interventions have limits. Over decades, even small failures accumulate. Systems drift. Materials fatigue. Human bodies age. The margin for error narrows. This does not make long-term space habitation impossible, but it makes it fragile. A lifetime in space would be a life lived in constant partnership with technology. Survival would depend not just on biology, but on machines that must function reliably for decades. On Earth, technology fails all the time without catastrophic consequences. In space, failure has fewer buffers. There is also the question of evolution. Over a single lifetime, genetic change is minimal. But over generations, space environments could exert selective pressures. Traits that support survival in microgravity or radiation-rich environments might become more common. For now, though, the focus remains on individual lifetimes. And within that frame, the human body presents clear constraints. The farther one goes, the longer one stays, the more pronounced these changes become. Distance amplifies duration. Duration amplifies biological consequences. This brings us back to the core question. How far could humans actually travel through space in a lifetime? The answer is not just about propulsion. It is about how long a body can function meaningfully under altered conditions. The Moon exposes these effects gently. Mars intensifies them. Beyond that, they compound. The body is not a passive passenger. It is an active participant in any journey. Over decades in space, it changes, adapts, and sets boundaries that no amount of ambition can ignore. Stranger than distance, stranger even than the quiet damage space does to the human body, is the way time itself begins to loosen its grip once motion becomes extreme. Up to now, time has behaved politely. A year has been a year. A decade has carried its familiar weight. Aging has felt predictable, even when the body changes faster than we would like. But relativity introduces a different possibility, one that feels less like science and more like a loophole written into the universe. Time, it turns out, does not pass at the same rate for everyone, everywhere. Under the right conditions, it can slow down, and for human space travel, that changes the meaning of a lifetime in a very specific, unsettling way. On Earth, we live inside a shared agreement about time. Clocks tick together, calendars line up. When someone says they waited an hour, everyone knows what that means. This shared rhythm exists because we are all moving through space at roughly the same speed and experiencing roughly the same gravitational field. The differences are so small they barely register. Relativity is always present, but its effects are too subtle to notice in daily life. Once speed increases dramatically, that quiet agreement begins to fracture. Einstein's theory of special relativity revealed something deeply unintuitive. Time is not absolute. It is not a universal background ticking away identically for all observers. Instead, time depends on motion. The faster you move through space, the slower you move through time, relative to someone who is moving more slowly. This is not metaphorical. It is not a trick of perception. It is a measurable, repeatable effect that has been confirmed countless times. Atomic clocks placed on fast-moving airplanes tick slightly more slowly than identical clocks left on the ground. Satellites must constantly correct for time dilation, or modern navigation systems would drift into uselessness within hours. At everyday speeds, the effect is tiny. At speeds approaching that of light, it becomes profound. Imagine a human aboard a spacecraft accelerating to a significant fraction of light speed. From their perspective, everything inside the ship feels normal. Their heartbeat feels steady. Their thoughts unfold at a familiar pace. Their aging feels unchanged. A year still feels like a year. But from the perspective of someone on Earth, watching that ship pass by, something strange happens. The traveller's clock runs slow. Their movements appear stretched. Their biological processes unfold more gradually. While the traveller experiences 1 year, Earth may experience many. This is time dilation. It creates an unusual trade. Distance can be crossed without consuming the traveller's subjective lifetime, but the cost is paid elsewhere. Time does not disappear. It shifts. For a human lifetime in space, this introduces a possibility that would otherwise be forbidden by distance alone. A person could, in principle, travel far beyond what would normally fit within their biological lifespan, as long as they are willing to move fast enough and accept that the rest of the universe will age without them. This is where relativity begins to feel like a strange gift. It does not let humans break the speed limit of the universe. Nothing with mass can outrun light, but it does allow humans to stretch their personal time, compressing years of travel into decades of a lived experience. However, this gift comes with conditions. First, acceleration matters. To experience strong time dilation, a spacecraft must reach extremely high speeds, close to that of light. Getting there requires enormous energy. Accelerating gently over long periods reduces stress on the body, but it still demands propulsion systems far beyond current capabilities. Second, deceleration matters just as much. Slowing down from relativistic speeds requires just as much energy as speeding up. Without a way to shed that velocity safely, arrival becomes impossible. A human lifetime spent accelerating without ever slowing down is not travel. It is exile. Third, the environment becomes increasingly hostile as speed increases. At near-light speeds, even sparse interstellar matter becomes dangerous. Collisions with individual atoms release enormous energy. Radiation intensifies. Shielding becomes a dominant design challenge. Relativity does not eliminate these problems. It simply reframes the timeline. There is also a psychological dimension that is often overlooked. Time dilation protects the traveller's biological clock, but it does nothing to protect their social clock. Relationships do not stretch. Cultures do not wait. Languages evolve. Civilizations rise and fall. A traveller who leaves Earth at high speed may return to find that everyone they knew is gone, not because of tragedy, but because of time. Their homeworld has moved on without them. From the traveller's perspective, this loss is compressed. They may remember people vividly, unchanged in memory. The shock comes at arrival, when familiar references no longer exist. The planet itself may look similar, but everything else has shifted. This is sometimes illustrated through the so-called twin scenario, where one twin remains on Earth while the other travels at high speed and returns younger. But the emotional reality of that situation is rarely explored. Being biologically younger than the world you left behind is not a neutral outcome. It creates dislocation. For a human lifetime, this raises an uncomfortable question. What does it mean to outlive your own time? Relativity allows a human to travel far in space without aging proportionally, but it does not allow them to bring their era with them. A lifetime stretched by motion becomes detached from the historical flow of the rest of humanity. This may be acceptable for some, others may find it deeply unsettling. There is also the matter of direction. Time dilation depends on relative motion. From the traveller's frame, Earth is moving fast. From Earth's frame, the traveller is moving fast. Both perspectives are valid, but only one experiences reduced aging relative to the other. This symmetry hides an asymmetry. The traveller must change frames by accelerating and decelerating. Those changes break the symmetry and determine who ages less. This is not just mathematical. It has physical consequences. Acceleration produces forces. It requires fuel. It places stress on structures and bodies. Over a lifetime, repeated acceleration phases would accumulate wear. Even if time dilation preserves youth, the act of moving fast enough to achieve it introduces its own costs. There's also gravitational time dilation to consider. Time runs more slowly in stronger gravitational fields. A clock closer to a massive object ticks more slowly than one farther away. This effect is real but modest unless gravity is extreme. In theory, a human could experience slower time by orbiting close to a massive object, such as a neutron star or black hole, while remaining safely outside destructive tidal forces. In practice, these environments are extraordinarily dangerous. Radiation, intense gravity gradients, and orbital instability make them poor candidates for long-term habitation. Even if such an arrangement were possible, it would again isolate the traveller from the rest of the universe's timeline. Time would pass more slowly for them, but faster elsewhere. Relativity therefore offers no free extension of life in a shared sense. It offers personal time at the expense of communal time. This distinction matters deeply when considering how far humans could travel in a lifetime. If lifetime is defined biologically, relativity expands the map. If lifetime is defined socially, culturally, or historically, relativity compresses it. A traveller moving near light speed may experience 30 years of life while Earth experiences centuries. That traveller's lifetime fits neatly within their own body, but not within the continuity of human history. This suggests that relativity changes not just the scale of travel, but the meaning of participation. A relativistic traveller is not simply going far, they are stepping out of sync. There is another subtle effect worth noting. At extreme speeds, distances in the direction of motion contract. This length contraction means that from the traveller's perspective, the universe ahead shrinks. Stars appear closer together along the direction of travel. The distance to a destination is reduced in the traveller's frame. This contributes to the feasibility of long journeys within a single lifetime. The universe effectively cooperates by shortening itself. But again, this cooperation is conditional. The traveller pays for it in energy, isolation, and environmental risk. Relativity does not turn the universe into a friendly place. It simply reveals that the rules are more flexible than classical intuition suggests. For human space travel, this flexibility introduces a fork in the road. One path stays slow, local, synchronized with Earth. The other goes fast, far, and out of phase with everything left behind. Neither path is inherently better. They serve different goals. A civilization focused on continuity, shared experience, and gradual expansion may favour the first. A civilization willing to trade synchronicity for reach may explore the second. For an individual human, the choice would be existential. To move fast enough to benefit from time dilation is to accept that you will not return to the same world you left, even if you return to the same planet. This is not time travel in the fictional sense. It is not jumping to a future that can be altered. It is simply arriving later than everyone else. From a lifetime perspective, relativity offers a strange compromise. It allows a person to cross distances that would otherwise demand many generations, but it does so by detaching that person from the shared timeline of humanity. This raises a final, quieter question. Is a lifetime measured by how long one lives, or by how long one belongs? Relativity answers the first generously. It answers the second not at all. For now, it is enough to sit with the strangeness of it. Time is not fixed. It bends, it stretches. It can be traded for speed and distance, but it never disappears, and it never forgets to take something with it when it gives. The universe allows us to go far, but it insists that we pay attention to how we define a life while doing so, still moving ahead. At a certain point, speed stops being the most important variable, and patience takes its place. When distances stretch beyond what even relativity can comfortably compress into a single human experience, the conversation shifts. Instead of asking how fast we can go, we begin asking how long we're willing to continue. This is where the idea of generation ships quietly enters the picture, not as a bold technological leap, but as a philosophical one. A generation ship is not designed to arrive within a lifetime. It is designed to keep going after the people who began the journey are gone. The concept is deceptively simple. Build a spacecraft large and stable enough to support human life indefinitely. Send it toward a distant star at a speed far below that of light. Accept that the journey will take centuries, perhaps millennia. The people who launch the ship will never see its destination. Their children might not either. Arrival becomes something abstract, a promise rather than an expectation. This idea feels unsettling because it challenges how humans normally relate to travel. We are accustomed to journeys having endpoints we can personally reach. Even long endeavours are framed with some version of completion. A generation ship refuses that framing. It asks people to commit to motion without closure. From a purely physical standpoint, generation ships solve a problem that propulsion cannot. If you cannot go fast enough to cross interstellar distances in one life, you can stretch the journey across many. You trade speed for continuity. The ship becomes less like a vehicle and more like a moving world. But the moment you do that, the meaning of travel changes. No one aboard is truly travelling in the everyday sense. They are living, being born, growing old, forming relationships, raising children, all within a structure that is always moving but never arriving, at least not for them. This raises an immediate question. Is that still travel, or is it something else entirely? A generation ship would need to be self-sustaining in a way no human habitat has ever been. Food production would have to be closed loop. Air and water recycling would need to operate flawlessly for generations. Energy systems would need redundancy beyond redundancy. There would be no resupply missions, no outside support. The ship would be its own ecosystem. From a technical perspective, this is daunting but not obviously impossible. We already understand many of the components involved. The challenge is not just building them, but ensuring they remain functional across timescales longer than most human institutions have ever survived. Technology ages, materials fatigue, software becomes obsolete, knowledge decays if not actively preserved and transmitted. Over centuries, even small inefficiencies can become existential threats. Then there is the human element. A generation ship is not crewed in the usual sense. The initial travellers may be astronauts or specialists, but their descendants will simply be residents. They will not have chosen the mission. They will have inherited it. This inheritance shapes everything. Children born aboard a generation ship would grow up with a sky that never changes, walls that define the universe, and a destination that exists only in stories and simulations. Earth would not be home. It would be history. The stars outside would be points of light without cultural meaning beyond what is taught. For them, the ship is the world. That world would need structure, governance, education, and culture. It would need ways to resolve conflict, distribute resources, and maintain social cohesion. Over generations, these systems would evolve, sometimes deliberately, sometimes accidentally. One of the central risks of a generation ship is not mechanical failure, but social drift. Values change, priorities shift. The original mission may lose relevance. A population that has never seen Earth and will never see the destination may begin to question why the journey matters at all. This is not a failure of character. It is a natural consequence of human psychology. Meaning is contextual. Without direct experience of either the origin or the endpoint, the journey itself must justify its continuation. Some have suggested that a generation ship would require a strong cultural or ideological framework to sustain purpose. Others argue that purpose would need to be flexible, allowing the mission to adapt to the lived reality of those aboard. Either way, the idea of never arriving is central. A generation ship demands acceptance that arrival is someone else's story. This creates a strange relationship with time. On Earth, we measure progress by milestones we can personally reach. On a generation ship, progress is generational. Success is defined by stability rather than achievement. The greatest accomplishment is continuity. From the perspective of an individual life, this is a radical shift. A person's contribution would not be measured by how far they travelled, but by how well they maintained the conditions for others to continue. This reframes what it means to go far in a lifetime. The distance covered by the ship might be immense, but the distance experienced by any one person would be minimal. They would spend their entire life within the same few kilometers of structure, and yet collectively humanity would be moving across interstellar space. There is also the question of consent. Can future generations meaningfully consent to a journey they cannot leave? On Earth, people can emigrate, change environments, seek novelty. On a generation ship, the environment is fixed. The option to opt out does not exist. This raises ethical concerns that do not have easy answers. Some argue that life aboard a well-designed generation ship could be rich, meaningful, and fulfilling, even without planetary variety. Others worry that confinement, no matter how well managed, imposes limits that no one should be born into. The truth likely lies somewhere in between. Humans have lived fulfilling lives in constrained environments before. Islands, remote regions, closed communities. But none of these were truly closed in the way a generation ship would be. Another challenge is population management. The ship's ecosystem would have a carrying capacity. Birth rates would need regulation. This introduces complex social and ethical questions. Who decides? How is compliance ensured? How are individual desires balanced against collective survival? Over decades, these decisions would shape culture in deep ways. Family structures might change. Concepts of personal freedom might adapt. Norms would evolve in response to the environment. Education would be critical. Knowledge of how the ship works, why it exists, and how to maintain it would need to be passed down reliably. Myths and stories would likely emerge alongside technical manuals. History would blur into narrative. Over centuries, the ship might develop its own identity, distinct from Earth. Language could shift. Accents form. Traditions arise that make sense only within the context of life in transit. At that point, the idea of arrival becomes even more complex. If the ship eventually reaches its destination, the people aboard may not see it as home. They may see it as disruption. Leaving the ship could feel like exile rather than fulfillment. This is one of the paradoxes of generation ships. The longer the journey lasts, the more the ship itself becomes the destination. From the standpoint of a human lifetime, generation ships represent the ultimate surrender of personal arrival in favour of collective motion. They allow humanity to cross distances that no individual could endure, but they do so by redefining what a journey is. In this model, a lifetime is not measured by how far you go, but by how well you sustain the going. This contrasts sharply with relativistic travel. where an individual stretches their own time at the cost of losing synchrony with the rest of humanity. Generation ships preserve synchrony within the ship, but abandon it with respect to Earth. Both approaches trade something fundamental. Generation ships also highlight an uncomfortable truth. If humanity wishes to reach other stars without invoking speculative physics or extreme relativistic effects, someone will have to accept never arriving. That acceptance runs counter to many cultural narratives about exploration. Heroes return, journeys conclude. Generation ships deny that closure. Instead, they offer continuity as the reward. The idea that humanity, as a process rather than a collection of individuals, can move outward. Whether this is inspiring or unsettling depends on how one defines meaning. For some, contributing to a future they will never see is already familiar. Parents do this, educators do this, scientists do this. A generation ship magnifies that logic to cosmic scale. For others, the absence of personal arrival may feel empty. A life spent maintaining a system for a goal that remains abstract can feel like deferral rather than fulfillment. Both reactions are valid. What matters for our broader question is this. Generation ships expand how far humans can travel, but they compress how far any one human can go. They solve distance by dissolving individual endpoints. They are not about speed. They are about endurance. Each of these ideas responds in its own way to the same tension. The universe is large. Human lives are finite. Something has to give. Generation ships choose to let the idea of arrival go while keeping life continuous. That choice may not be comfortable, but it is honest. And honesty matters when considering the true limits of human travel. Sometimes, going farther means accepting that the journey itself is the destination, not just for a moment, but for generations. Rather than stretching a journey across generations, there is another idea that keeps returning whenever humans confront distances that feel too large for a single life. Instead of letting time pass for many people, what if we could pause it for one? Not stop it entirely perhaps, but slow it enough that the years of travel no longer consume a lifetime in the usual way. This is where cryogenic sleep enters the conversation, carrying with it a particular kind of hope. Not the hope of arriving quickly, but the hope of arriving unchanged. The basic intuition behind cryogenic sleep is simple and deeply human. We already associate sleep with time passing unnoticed. A long night can vanish in what feels like moments. Extend that logic, and it becomes tempting to imagine a voyage where decades pass externally, while the traveller experiences almost none of it. The ship moves, time advances, but the person inside remains suspended, borrowing time rather than spending it. In practice, the idea is far more complicated. Human bodies are not designed to be paused. Life is a continuous process of chemical reactions, electrical signals, cellular repair, and waste removal. Interrupt those processes too aggressively, and damage accumulates. Cooling a body slows metabolism, but it also introduces risks. Ice crystals can form inside cells, membranes can rupture, proteins can denature, tissues can be injured in ways that are not immediately visible. Medicine already uses controlled cooling in limited ways. During certain surgeries, patients are cooled to reduce metabolic demand and protect organs. This works because the duration is short and carefully managed. Even then, risks remain. Extending this state from hours to months or years introduces challenges that current science cannot yet fully resolve. Still, the appeal persists because cryogenic sleep offers something generation ships do not. It preserves the individual narrative. The person who leaves is the person who arrives. They do not age into a different era. They do not become a relic of a forgotten past. Their relationships, skills, and sense of self remain intact, at least in principle. This preservation of identity is powerful. From the perspective of a human lifetime, cryogenic sleep transforms distance into something closer to inconvenience. A century-long journey becomes a brief interruption in consciousness. The traveller sacrifices awareness, not years of lived experience. But awareness is not an optional feature of being human. It is where meaning forms. To give it up for long stretches is not a neutral act. Consider what it would feel like to enter cryogenic sleep. You would prepare for departure knowing that the next moment of consciousness might occur decades later. Everyone you know would continue aging. Civilizations would continue evolving. Languages might shift. Technology might advance beyond recognition. When you wake, you would be out of time, not just out of place. This temporal dislocation carries psychological weight. Even if the body survives intact, the mind must reconcile the gap. Memory would feel recent. Emotional attachments would feel unresolved. Grief might arrive all at once, compressed into the moment of waking. There is also the question of trust. Entering cryogenic sleep requires extraordinary faith in systems that must function autonomously for years or centuries. Life support must remain stable. Monitoring must detect and correct problems without human intervention. Power must never fail. Maintenance must be either unnecessary or automated to a degree far beyond what we currently achieve. A generation ship distributes risk across many people and many moments. Cryogenic sleep concentrates it. A single failure during suspension could be fatal, and the sleeper would never know it was coming. What makes cryogenic travel fragile in a different way? It relies on uninterrupted technological perfection. Over long durations, perfection is a high bar. There is also the biological unknown. Even if freezing and rewarming techniques are perfected, we do not yet know how long-term suspension affects complex systems like the brain. Memory is not stored in a single place. It is encoded in patterns of connectivity, chemical gradients, and ongoing activity. Pausing that activity may preserve structure, but whether it preserves subjective continuity is unclear. Waking up might feel like stepping forward in time, or it might feel like something subtler has been lost. Then there is aging. Cryogenic sleep aims to halt or dramatically slow biological aging. But aging is not just the accumulation of damage over time. It is also influenced by genetic programs, cellular clocks, and systemic interactions. It is possible that some aspects of aging continue even at low metabolic rates. If so, a person might wake having aged biologically, even if they did not experience that aging consciously. The borrowed time would not be free. Still, compared to the alternative of spending decades awake in confinement, cryogenic sleep remains attractive. A person asleep does not experience isolation. They do not experience monotony. They do not need social structures to maintain morale. Their psychological endurance is irrelevant. This simplicity is seductive. Cryogenic sleep also aligns well with the realities of the deep space. Long journeys involve long periods of inactivity. Coasting between stars offers little to do. Systems checks, navigation, and maintenance could be automated. The presence of awake humans during those stretches may not add value. In that sense, cryogenic sleep is not just about preserving lifetimes. It is about matching human presence to moments when it matters. However, this raises another subtle question. If most of the journey is spent unconscious, is the journey still part of the life? Or is it more like a discontinuity, a gap where life is paused and resumed? From a narrative perspective, cryogenic sleep fractures experience. The story of the journey is no longer continuous. It becomes two separate lives bridged by a technical procedure. Some might welcome that. Others might find it unsettling. There is also the ethical dimension. Who decides when to wake someone? Under what conditions? If a destination turns out to be unsuitable, does the sleeper remain asleep indefinitely? Does someone else decide that their journey should end without their participation? These questions become especially complex if multiple people are suspended together. Coordination, consent, and contingency planning take on new forms. Cryogenic sleep also does not eliminate the need for generational thinking entirely. Someone must remain awake to oversee systems, or systems must be reliable enough to require no oversight. Either way, human presence does not disappear entirely, it shifts roles. In some visions, crews rotate between wakefulness and sleep. A few remain active while others rest. Over time, roles switch. This distributes risk and experience. It also creates a strange social structure, where people share a journey but not the same years of it. Friendships would span discontinuous time. A person might say goodbye to someone entering sleep and greet them decades later, having aged significantly in the meantime. Relationships would become asymmetric in time, even if they remain emotionally intact. This asymmetry complicates identity. Who are you in relation to someone who remembers you as you were, while you remember them as they used to be? Time becomes uneven within the same community. In contrast to relativistic time dilation, where time differences arise from physics, cryogenic sleep creates time differences by choice. It is a voluntary desynchronization. That voluntariness is important. It gives agency, but it also creates responsibility. Choosing to sleep through decades is a choice to disengage from the unfolding of events. Some will see that as practical. Others will see it as avoidance. Cryogenic sleep also assumes that the future is desirable. You sleep in the hope that waking will be worthwhile, that the destination exists, that society remains functional, that the journey has meaning. This hope is not guaranteed. Still, compared to generation ships, cryogenic sleep keeps the focus on individual lifetimes. It says that a human life should not be diluted across centuries of maintenance and inheritance. It says that arrival matters and that it should be personally experienced. This aligns strongly with how humans typically define fulfillment. There is another advantage. Cryogenic sleep reduces exposure to many of the bodily harms discussed earlier. Reduced metabolism means reduced radiation damage per unit of subjective time. Muscle atrophy is irrelevant if muscles are not being used, provided they can be restored. Psychological stress vanishes while unconscious. In this way, cryogenic sleep sidesteps many of the problems of long-term space habitation by removing habitation from the equation. But it introduces its own fragility. The sleeper becomes entirely dependent. Agency is surrendered in exchange for preservation. From a lifetime perspective, cryogenic sleep offers a bargain. You give up years of awareness. In return, you gain distance without aging. Whether that bargain is acceptable depends on how one values experience. Is living defined by time alive or by time remembered? Is a life with large gaps still whole? These are not scientific questions. They are human ones. Cryogenic sleep does not solve the speed limit. It does not shorten distances. It simply removes the traveller from the timeline while those distances are crossed. The universe still takes as long as it takes. In that sense, cryogenic sleep is not about conquering space. It is about negotiating with time. Cryogenic sleep stands out because it does not ask humanity to change its structure or redefine its values entirely. It asks individuals to pause, to trust, and to wake later. Whether that is a gift or a loss remains open. What it clearly represents is another way humans might travel farther than biology alone would allow, not by moving faster, but by stepping aside while time does its work, then returning to consciousness as if no time had passed at all, even though the universe has moved on without them, continuing its steady motion forward. Picture for a moment a single person sealed inside a vessel that is no longer drifting gently but accelerating with purpose, pushing closer and closer to the ultimate boundary the universe allows. This is not the slow patience of generation ships or the quiet surrender of cryogenic sleep. This is motion taken seriously. Near-light speed does not just change how far someone can go, it changes what far even means. At everyday scales, distance and time feel inseparable. 10 kilometers takes longer to cross than 1. A year is a fixed slice of life. But as speed increases toward that of light, this familiar relationship begins to warp. Space contracts. Time stretches. A journey that would normally outlast many human lives starts to fit, strangely and counterintuitively inside one. The first thing to clarify is what near light speed actually implies. Light travels at a fixed speed in a vacuum, and nothing with mass can reach or exceed it. But physics allows motion arbitrarily close to that limit. 90% of light speed is allowed, 99% is allowed, even 99.999% is allowed in theory. Each additional decimal place, however, demands exponentially more energy. At these speeds, the universe behaves very differently for the traveller than it does for those left behind. From the outside, watching from Earth, the traveller's ship would appear to be racing away, its clocks ticking slowly, its movement stretched. Years would pass on Earth while months or even weeks passed on board. From the traveller's perspective, everything inside the ship would feel normal. Heartbeats would remain steady. Thoughts would unfold at a familiar pace. Aging would feel unchanged. This difference is not an illusion. It is the result of time dilation, a core consequence of relativity. Time itself becomes elastic, dependent on motion. Now consider what this means for distance. At near-light speed, distances in the direction of travel contract from the traveller's point of view. A star that is 10 light-years away from Earth does not feel 10 light-years away to someone moving toward it at extreme speed. The universe compresses along the direction of motion. What remains unchanged is the speed of light itself. What changes is how much space exists between here and there, depending on who is measuring it. This contraction is what allows a single human to cross staggering distances within their own lifetime. For example, imagine a traveller accelerating steadily at 1 Earth gravity, a comfortable and survivable level, for about 1 year. By the end of that year, they would be moving at a significant fraction of light speed. Continue accelerating for a few more years, then flip the ship and decelerate symmetrically near the destination. This kind of profile minimizes stress on the body while maximizing relativistic effects. Under such conditions, a human could, in principle, reach stars dozens or even hundreds of light-years away, while experiencing only decades of subjective time. From Earth's perspective, centuries or millennia would pass, but the traveller would age modestly. This is the strange arithmetic of near-light travel. Distance becomes something you can trade against everyone else's time, not your own. So how far could one human actually go this way? The answer depends on how much time they are willing to lose with respect to the rest of humanity. Within a single subjective lifetime, perhaps 50 or 60 years of experienced time, a traveller could reach not just nearby stars, but a significant portion of the Milky Way. Tens of thousands of light-years become accessible. The galactic centre, normally unreachable on human timescales, could be visited within one person's life, from their own perspective. In extreme scenarios, a traveller could even cross the entire galaxy within a single lifetime, aging only a few decades while hundreds of thousands of years pass elsewhere. This sounds like science fiction, but it follows directly from known physics. No speculative engines, no exotic matter, just relentless acceleration and the universe's own rules. However, the costs are severe. First, energy. Accelerating a human-sized spacecraft to near-light speed requires energy comparable to that produced by entire civilizations over long periods. This is not a matter of efficiency improvements. It is baked into the equations. The closer you get to light speed, the more energy is required for each tiny increase. Second, shielding. At near-light speed, even the sparse interstellar medium becomes a hazard. Individual hydrogen atoms strike the ship with energies equivalent to high-energy radiation. Dust grains become catastrophic projectiles. Without extraordinary shielding and deflection systems, the ship would be destroyed. Third, navigation. At these speeds, tiny errors compound rapidly. Course corrections require enormous energy. Reaction times shrink. The universe ahead is not static. Stars move. Gas clouds drift. Precision becomes unforgiving. Fourth, isolation. Near-light travel maximizes temporal separation. A traveller who goes far enough will return, if they return at all, to a civilization utterly unrecognisable. Languages would be different. Cultures would have evolved. The traveller would be a relic of a forgotten past, biologically young but historically ancient. This is not a side effect, it is the core consequence. A human who travels near light speed is not just leaving Earth, they are leaving their era. This makes near-light travel a deeply personal choice. It is not exploration in the usual sense. It is self-removal from the shared timeline of humanity. There is also the question of return. While reaching distant regions of space may fit within a lifetime, returning to Earth requires another long acceleration and deceleration sequence. By the time the traveller comes back, if they do, Earth may have changed beyond recognition, or may no longer exist in any familiar form. The farther one goes, the less meaningful return becomes. There is also the biological question. Even if time dilation preserves youth, the body still experiences acceleration forces. A sustained one-gravity acceleration is tolerable, but decades of it would place continuous stress on bones, muscles, and cardiovascular systems. This is survivable in theory, but never tested. Radiation remains an issue as well. High-speed travel through interstellar space exposes the traveller to intense fluxes of energetic particles. Even with shielding, cumulative exposure over decades could be significant. Then there is the psychological burden. A lifetime spent knowing that everyone you have ever known will age and die while you continue forward carries weight. Even if communication is technically possible, delays grow enormous. Conversations become historical documents rather than exchanges. Near-light speed offers reach at the cost of belonging. From the perspective of the traveller, the universe becomes smaller. Stars draw closer. Distances shrink. Time feels generous. From the perspective of everyone else, the traveller becomes increasingly distant, frozen in slow motion, slipping out of relevance. This duality is unavoidable. It also reframes the idea of achievement. If one human can cross the galaxy in a lifetime but never meaningfully share that experience with others, what has been gained? Knowledge, perhaps? Perspective? A witness? Near-light travellers would be less like explorers returning with stories and more like messages sent into the future, carrying a snapshot of humanity forward in time. There is also a limit even here. The universe is not static, it is expanding. Beyond a certain distance, galaxies are receding faster than light due to the expansion of space itself. No amount of speed allows you to catch up. There are regions of the universe that are permanently unreachable, even in principle. Near-light travel cannot conquer cosmic expansion. It can only operate within its bounds. So how far could one human go? Farther than intuition allows, farther than any other method permits within a single lifetime. Across star systems, across the galaxy, perhaps even approaching its far edges, but not everywhere, and not without sacrifice. Near-light speed turns a human lifetime into a narrow, fast-moving slice through space-time. It maximizes distance while minimizing experienced time. It does not maximize shared life. In that sense, it represents one extreme solution to the problem of cosmic scale. Generation ships sacrifice individual arrival. Cryogenic sleep sacrifices awareness. Near-light travel sacrifices synchrony. Each approach preserves one aspect of human life by giving up another. Near-light travel preserves the continuity of consciousness and identity. You remain yourself. You remain awake. You experience the journey, but you lose the world you came from. Whether that is acceptable depends on what one believes a life is for. Some might see this as the ultimate expression of curiosity, to go farther than anyone else, to see the galaxy firsthand, even if no one you know will ever understand what you saw. Others might see it as loneliness, elevated to cosmic scale. What matters for our broader question is this. Physics does allow a single human to go astonishingly far within one lifetime, provided that lifetime is defined biologically and subjectively rather than socially. Near-light speed does not solve the problem of distance cleanly. it simply shifts where the cost is paid. Long after planets stop feeling like destinations and stars become the next points of reference, there is a quieter boundary that deserves attention. It is not marked by a dramatic change in scenery or a sudden emptiness. It is simply the place where the sun's influence fades enough that the solar system can no longer convincingly claim you as its own. Leaving the solar system sounds decisive, almost ceremonial, but in reality it is a slow, understated transition. And whether a human could cross that boundary within a lifetime depends very much on how we define both leaving and lifetime. The solar system does not end where the planets do. Beyond Neptune lies the Kuiper Belt, a wide, diffuse region filled with icy bodies and remnants from the early days of planetary formation. Beyond that, farther still, is the scattered disk, where objects follow long, tilted orbits influenced by passing stars and the galaxy itself. And beyond even that is the Oort cloud, a vast spherical halo of debris that may extend tens of thousands of astronomical units from the Sun. None of these regions has a clear edge. They fade gradually. Gravity weakens with distance but never truly disappears. The Sun's pull becomes subtle, then marginal, then comparable to the tug of nearby stars and the collective mass of the Milky Way. Leaving the solar system is not a single event. It is a prolonged loosening. From a human perspective, this makes the question more slippery. Are you leaving the solar system when you pass the orbit of Neptune? When solar wind pressure gives way to interstellar plasma? When the sun's gravity no longer dominates your trajectory? Each definition produces a different answer. For spacecraft, the boundary is often marked by the heliopause, the region where the solar wind slows and merges with the interstellar medium. This is where the bubble of charged particles emitted by the Sun finally thins enough to allow the galaxy to press back. Voyager 1 crossed this boundary in 2012. Voyager 2 followed in 2018. These spacecraft are the only human-made objects to have done so. They offer a sobering reference point. Voyager 1 was launched in 1977. It took 35 years to reach the heliopause. At the time of crossing, it was travelling at about 17 kilometers per second relative to the Sun. That is fast by spacecraft standards, but painfully slow by interstellar ones. At that speed, Voyager will take tens of thousands of years to reach even the nearest stars. Now consider a human lifetime, even a long one, 80 years, perhaps 90. Within that span, Voyager would not have even completed a quarter of its journey to the heliopause. This seems to suggest that leaving the solar system within a lifetime is impossible, and with current technology, for humans, that conclusion is essentially correct. Chemical rockets, even when assisted by gravity slingshots, cannot accelerate human-carrying spacecraft fast enough to cross the outer boundaries of the solar system in a reasonable fraction of a life. The distances are simply too large. The acceleration phases are too short. Once fuel is expended, the ship coasts. But the story does not end there because lifetime is not a fixed quantity in all frames of reference. If we return to the relativistic effects discussed earlier, the picture begins to change. At near-light speeds, time dilation allows a traveller to experience less time while covering more distance. Length contraction reduces the perceived distance ahead. These effects do not eliminate the solar system's size, but they change how that size fits into a personal timeline. So the question becomes more precise. Could a human, travelling fast enough, cross the outer limits of the solar system within their own experienced lifetime, even if centuries pass elsewhere? In principle, yes. At relativistic speeds, the solar system becomes surprisingly small. The distance to the heliopause, roughly 120 astronomical units, is trivial compared to interstellar distances. At even a modest fraction of light speed, a traveller could cross it in days or weeks of subjective time. From the traveller's perspective, leaving the solar system would not feel like a long journey at all. It would feel like a brief transition. The sun would shrink behind them. The density of solar particles would drop. Instruments would detect a change in environment, and that would be that. But this framing hides an important distinction. Leaving the solar system physically is not the same as leaving it meaningfully. The solar system is not just a region of space, it is an environment shaped by familiarity, infrastructure, and reference. Even far beyond the orbit of Neptune, the Sun remains a bright dominant presence. Its light still warms, its gravity still organises motion, its influence is still felt. True departure is psychological as much as physical. For a human traveller, leaving the solar system would be the moment when the Sun stops being the centre of experience. When it becomes just another star, no longer brighter or more important than the others. That shift takes distance, not just speed, and that distance, even at high velocity, implies time. For a human lifetime defined biologically, relativistic travel allows this shift to occur quickly. For a lifetime defined socially or historically, it does not. Earth would recede into the past long before the Sun receded into insignificance. This again raises the issue of perspective. A traveller might leave the solar system within a few years of personal time, while the civilization they left behind experiences generations passing before the same milestone is reached. So yes, one human could leave the solar system within a lifetime, if lifetime is defined narrowly and motion is extreme. But what would that actually mean for the person? Leaving the solar system marks the end of any reasonable possibility of return within a shared timeline. Once you commit to the velocities required to make this journey fit inside a single life, you also commit to temporal separation. By the time you could turn around, decelerate, and come back, Earth would be unrecognizable or gone. Leaving the solar system becomes a one-way transition, not because physics forbids return, but because time does. There is also the question of environment. The interstellar medium is not empty. It is thin, but it is active. Charged particles, magnetic fields, and radiation fill the space between stars. The solar system's heliosphere acts as a partial shield against some of these influences. Beyond it, exposure increases. For a human traveller, this means that leaving the solar system is also leaving behind a layer of protection. Shielding becomes more critical. Systems must operate without the Sun's support. Energy must be carried or generated internally. Navigation becomes more complex as familiar reference points fade. Psychologically, the act of leaving the solar system would carry weight. Even for someone who understands the physics, there is something deeply ingrained about the Sun as home base. It has been the centre of every human story that has ever existed. To see it diminish until it is indistinguishable from other stars would be to cross a symbolic threshold no one has crossed before. This is why the idea resonates so strongly. Leaving the solar system feels like leaving the family home of the species. Within a lifetime, that act would be less about distance than about choice. A choice to accept permanent separation. A choice to define one's life not by return but by continuation. There are other, less extreme ways a human lifetime could brush against this boundary. Without relativistic speeds, a person could participate in missions that move steadily outward, spending decades travelling through the outer solar system, never quite leaving, but always nearing the edge. Such a life would still feel profoundly distant from Earth, even if the heliosphere remains intact. A person could grow old aboard a vessel that never turns around, watching the sun slowly dim year by year, knowing that it will never vanish entirely during their lifetime, but also knowing it will never grow closer again. That too is a kind of leaving. It is also worth remembering that the solar system itself is not static. Over long timescales, it moves through the galaxy. The Sun carries its planets along as it orbits the Milky Way. In that sense, the entire solar system is already on an interstellar journey. We're all aboard a generation ship of sorts, whether we acknowledge it or not. Leaving the solar system within a lifetime, therefore, has two meanings. One is physical departure from the Sun's domain. The other is experiential departure from the assumptions that domain provides. The first may be achievable under extreme conditions. The second may occur much sooner. A human who spends decades beyond Mars, isolated, dependent on artificial systems, and unable to return easily, has already left the solar system in a meaningful way. even if gravity and solar wind still reach them. Their life no longer follows the rhythms Earth and the Sun impose, so when we ask whether a human could leave the solar system within a lifetime, the honest answer is layered. With current technology and normal definitions of time, no. The distances are too large, the speed's too slow. With relativistic travel and a willingness to abandon shared time, yes. Easily even. With psychological and cultural definitions many already have in smaller ways. Leaving the solar system is not just a matter of crossing a line, it is a matter of shedding context, and context is heavy. The farther we go, the more of it we must leave behind. Names, memories, expectations, histories. The solar system is not just where we live, it is how we think. Crossing its boundary within a lifetime would mean redefining what a lifetime is for. Is it for belonging or for witnessing? For continuity or for reach? That question does not have a single answer. Different people, different eras, different cultures would answer differently. What remains consistent is this. Leaving the solar system is not the end of a journey. It is the point where journeys stop being anchored to a familiar centre. After that, everything becomes relative in a deeper sense. Stars replace planets as destinations. The galaxy replaces the sun as reference. Time stretches unevenly. Lives become thinner threads, stretched across vast distances. Whether any human could ever reach another star is the question where imagination finally collides head-on with scale. Up to this point, the discussion has lived in a space where distances are vast but still familiar. The moon can be pictured, Mars can be mapped. Even the edge of the solar system, though enormous, remains conceptually tied to the sun. Another star is different. It represents a break so complete that intuition stops being useful. Between stars lies not just emptiness, but time in quantities that strain what a human life can reasonably contain. The nearest star system to Earth, Alpha Centauri, sits a little over 4 light-years away. On paper, that number looks manageable. 4 is small. Years are familiar. But a light-year is not a year in the ordinary sense. It is the distance light travels in a year, and light is the fastest thing the universe allows. Even at that speed, 4 years must pass before anything arrives. For anything slower, the clock stretches quickly. With the fastest spacecraft humans have ever built, reaching Alpha Centauri would take tens of thousands of years. Even optimistic projections using propulsion methods that do not yet exist still struggle to bring that down below several centuries. This is the core difficulty. Stars are not just far, they are far in a way that resists compression by technology alone. So when we ask whether any human could ever reach another star, we're really asking which definition of human and which definition of reach we are willing to accept. If we restrict ourselves to conventional lifetimes, ordinary biology, and non-relativistic speeds, the answer is straightforward. No, the distance is too large. The time required is far greater than a single life can support, even under ideal conditions. But humans are rarely satisfied with straightforward answers. Relativity complicates this picture in a way that is both promising and unsettling. As explored earlier, near-light speed travel allows a human to experience less time while crossing vast distances. From the traveller's perspective, a journey to Alpha Centauri could take only a few years if their ship accelerates close enough to the speed of light. The universe ahead would contract. Time would slow. The distance would shrink in lived terms. From Earth's perspective, however, the journey would still take years. More importantly, the return would be impossible without even more time passing. A traveller who reaches another star this way has not escaped time. They have simply shifted where it is paid. So yes, in principle, a human could reach another star within their own lifetime if they travel fast enough. The physics allows it. Nothing in relativity forbids it. But this answer hides several layers of cost. First is energy. Accelerating a human-carrying spacecraft to relativistic speeds requires energy on a scale that dwarfs anything humanity has ever produced. It is not a matter of incremental improvement, it is a qualitative leap. Even harnessing the output of entire planets would barely begin to cover the demand. Second is survival. At near-light speeds, space becomes hostile in a new way. Interstellar gas atoms strike with the energy of radiation. Dust grains become lethal. Shielding must be nearly perfect. One failure could end the journey instantly. Third is arrival. Reaching another star is not just about getting there. It is about slowing down. Deceleration requires as much energy and precision as acceleration. Without it, a traveller would pass through the destination system at relativistic speed, unable to stop, unable to interact, unable to meaningfully reach anything. So even if the journey fits inside a lifetime, the engineering burden remains enormous. There is also the question of what happens upon arrival. Another star is not a welcoming place by default. Planets may or may not exist. Those that do may be hostile. Radiation environments could be extreme. Gravity could be incompatible with human health. Even reaching another star does not guarantee a place to stand, breathe, or live. In that sense, reaching another star does not automatically mean survival beyond arrival. Then, there is the psychological dimension, which cannot be separated from the question. A human who reaches another star via relativistic travel will arrive in a future that is no longer theirs. Earth will have moved on. Everyone they knew will be gone. Cultures will have changed beyond recognition. The traveller will be biologically young but historically ancient. This creates a form of isolation that has no earthly analogue. The traveller is not just far from home. Home no longer exists in any meaningful sense. For some, this might be acceptable. For others, it would hollow the achievement. An alternative approach avoids this extreme isolation by abandoning the idea of a single human reaching another star consciously. Generation ships attempt this by distributing the journey across many lives. Cryogenic sleep attempts it by pausing individual experience. Each of these strategies answers the distance problem by redefining what it means to arrive. In a generation ship, no one person reaches another star. Humanity does. The cost is that arrival belongs to descendants, not the originators. The journey becomes a shared inheritance rather than a personal experience. In cryogenic sleep, an individual reaches another star biologically intact, but not experientially continuous. Decades or centuries vanish from consciousness. The traveller arrives as themselves, but not as someone who lived the journey. Both approaches make arrival possible in different senses, but neither preserves all aspects of what humans usually mean by travel. There is also the possibility that future humans will no longer be bound by present biological constraints. Life extension, cybernetic augmentation, or digital consciousness could stretch what we consider a lifetime. If a human can live for centuries or millennia, interstellar distances become less prohibitive. However, this shifts the question again. At what point does a human cease to be human in the traditional sense? Extending life indefinitely changes psychology, motivation, and identity. A being that lives for thousands of years may not experience meaning, urgency, or attachment in the same way. So even if another star becomes reachable within an extended lifespan, the traveller may not resemble us closely enough to satisfy the spirit of the question. There is also the subtle issue of purpose. Why reach another star at all? On Earth, exploration has been driven by survival, resources, curiosity, and competition. In space, survival does not demand interstellar travel. Resources are abundant closer to home. Curiosity can be satisfied observationally. Competition loses meaning when distances span centuries. Reaching another star would be an act of intention rather than necessity. That intention must be strong enough to justify the cost. For a single human, the motivation would have to outweigh permanent separation from their species. That is a high threshold. It is possible that the first human to reach another star will not go as an explorer but as a caretaker, someone sent to seed knowledge, observe long-term processes, or act as a bridge between eras. In that sense, the traveller becomes less an adventurer and more a living artifact. This reframes arrival again. Reaching another star may not feel triumphant. It may feel quiet, lonely, purposeful, but heavy. There is also the question of whether reaching another star is even necessary for humanity's future. The solar system contains vast resources. Artificial habitats could support trillions of lives. Virtual environments could satisfy experiential desires. Expansion outward may be more symbolic than practical. If that is the case, interstellar travel becomes something humans do because they can, not because they must. And that distinction matters. So could any human ever reach another star? If the question means physically arrive there with their own body, within their own experienced lifetime, then yes, in principle, relativity allows it. The laws of physics do not forbid it. If the question means arrive there while remaining part of the same historical flow as Earth, then no. Distance makes that impossible. If the question means arrive there in a way that preserves biology, psychology and continuity all at once, then we do not yet know. Every proposed solution preserves some aspects of humanity by sacrificing others. This suggests that the question itself may be slightly misframed. Reaching another star may not be a single achievement, but a collection of partial ones. Knowledge reaches first, signals follow, machines arrive, humans follow in altered forms. The first human presence at another star may not look like a person stepping onto a surface. It may look like a consciousness waking from suspension, or a descendant born far from Earth, or a traveller emerging from relativistic isolation into a world that no longer remembers where they came from. In each case, arrival happens, but not in the way we instinctively imagine. What remains consistent is this: another star is not just far away, it is far away in time. Any human who reaches one must negotiate that fact, whether through patience, technology, or acceptance of separation. Distance demands trade-offs. Stars demand commitment. So the honest answer is layered, not definitive. A human could reach another star, but doing so would require redefining what a lifetime is, what belonging means, and what kind of story that life is meant to tell. Distance in space is usually described with numbers, kilometers, astronomical units, light years. These measurements are precise, objective, and emotionally empty. They tell you how far something is, but they do not tell you what that distance does to a person. Psychological distance operates on a different scale. It stretches and compresses independently of physical space, shaped by isolation, time delay, unfamiliar environments, and the slow erosion of reference points that once anchored identity. Long before a spacecraft runs out of fuel or a body reaches its biological limits, the mind begins to register how far away it truly is. On Earth, distance is softened by connection. Even when someone travels far, communication is immediate. Voices arrive without delay. Faces appear on screens in real time. Shared events happen together regardless of location. Psychological distance remains small because time remains synchronized. Space travel disrupts this synchronization first, and once it does, distance takes on a new quality. The earliest astronauts experienced only mild versions of this effect. Low Earth orbit keeps communication delays nearly imperceptible. Earth remains large, familiar, and visually present. The planet fills windows. Continents drift beneath. Home feels close, even when unreachable. Psychological distance remains manageable because sensory reminders are constant. As missions extend farther, those reminders weaken. On the Moon, Earth is still visible, but smaller. Communication delays are noticeable, though not disruptive. The sense of separation sharpens, but it remains reversible. Astronauts know they are days away, not months or years. The mind can tolerate that. Mars changes the equation. Earth becomes a point of light. Communication delays turn conversations into exchanges. Responses arrive long after emotional moments have passed. Laughter, reassurance, shared silence. all lose their immediacy. The brain, which evolved to regulate emotion through real-time social feedback, must adapt to absence. This adaptation is not dramatic at first. It begins subtly. Messages become more formal. Emotional nuance thins. People stop sharing small details because the delay makes them feel outdated by the time they arrive. Over time, communication shifts from living dialogue to archival record. That shift creates psychological distance even when emotional attachment remains strong. Relationships continue, but they no longer evolve together. The traveller changes in one direction, Earth changes in another. Each update reveals how far apart those paths have grown. Isolation amplifies this effect. Spacecraft and habitats are confined environments with limited sensory variety. The same walls, the same sounds, the same routines. On Earth, monotony is broken by incidental novelty. A walk outside, a new face, a change in weather. In space, novelty must be manufactured intentionally, and even then its impact fades with repetition. Over months, the brain adjusts. Over years, it reorganizes. Attention narrows. Emotional range can flatten. Small frustrations take on disproportionate weight because there is nowhere for them to dissipate. This is not a failure of resilience. It is a predictable response to sustained confinement. Psychological distance also grows from temporal mismatch. A traveller moving at relativistic speed or emerging from cryogenic sleep does not share the same timeline as those who remained behind. They are not just far away, they are out of sync. Events that feel recent to them are ancient to others. Cultural references lose meaning. Shared memories no longer overlap. This temporal distance can be more disorienting than physical separation. Humans rely on shared context to feel oriented. When context dissolves, identity becomes unstable. Who you are depends partly on when you are. Remove that anchor and the self must rebuild. Even without relativistic effects, long missions create temporal drift. A person spending decades away from Earth misses entire arcs of history. Political systems change, social norms evolve, language shifts subtly. When communication is delayed or infrequent, these changes are not absorbed gradually. They arrive in chunks, each one widening the psychological gap. There is also the loss of consequence. On Earth, individual actions ripple outward through social networks. In deep space, the circle of consequence is small. The same people see the same behaviours every day. External feedback is limited. Over time, this can distort self-perception. A person may feel simultaneously hyper-observed and invisible. This paradox strains mental health. Privacy becomes scarce. Anonymity disappears. Yet recognition from the broader human community fades. The mind struggles to reconcile being constantly seen by a few while effectively unseen by the many. Purpose plays a central role in buffering psychological distance. Missions with clear, meaningful goals tend to produce better psychological outcomes. Tasks provide structure. Progress creates momentum. However, over very long durations, even meaningful work can lose its immediacy. Goals feel abstract when completion lies years away. When arrival itself is uncertain or belongs to another generation, purpose must be sustained through belief rather than experience. That belief can be strong, but it requires reinforcement. Without it, motivation erodes quietly. Another subtle contributor to psychological distance is the loss of future projection. On Earth, people imagine futures that feel reachable, events next year, next decade, retirement, family milestones. In deep space, the future becomes constrained. Plans narrow. Possibilities contract. The mind, which uses future imagery to regulate present emotion, loses an important stabilizer. This does not always result in distress. Sometimes it produces acceptance, a focus on the immediate, a present-oriented mindset. For some individuals, this can be calming. For others, It feels like a slow suffocation of possibility. Memory also behaves differently under isolation. Without frequent external cues, memories can become dominant. The past grows vivid. Early experiences replay with unusual clarity. Nostalgia intensifies. This can be comforting at first, but over time it can anchor attention backward rather than forward. In extreme cases, identity begins to orient around memory rather than growth. The person becomes a caretaker of their past self, preserving who they were rather than evolving into who they might become. Psychological distance is also influenced by perceived irreversibility. Knowing that return is impossible or unlikely alters emotional processing. On Earth, even difficult experiences are softened by the knowledge that circumstances can change. In deep space, finality weighs heavily. Choices feel permanent. Mistakes feel amplified. This awareness can lead to heightened caution, but it can also lead to emotional withdrawal. When the cost of emotional investment feels too high, the mind may protect itself by narrowing attachment. Over decades, this can reshape personality. Individuals may become more self-contained, less reactive, more internally regulated. These changes are not inherently negative, but they mark a divergence from Earth normative psychology. Community dynamics also evolve. Small groups under long-term isolation develop distinct social patterns. Roles solidify, conflicts recycle, hierarchies emerge. Over time, these dynamics can feel claustrophobic, especially when no external social comparison exists. The psychological distance between crew members can paradoxically increase even as physical distance decreases. Familiarity does not guarantee intimacy. Proximity can magnify differences rather than erase them. This is why selection and training matter so much. Psychological compatibility, adaptability, and emotional regulation are not secondary traits in space travel. They are central survival factors, yet even the most compatible group cannot eliminate psychological distance entirely. Distance is baked into the environment. Space does not provide the feedback loops that human minds evolved to expect. There is also the existential dimension. Space strips away many of the distractions that buffer humans from larger questions. Why am I here? What does this matter? Who will remember this? These questions surface naturally in isolation, and without cultural noise to drown them out, they linger. For some, this leads to clarity, a sharpened sense of meaning. For others, it leads to doubt. Meaning becomes fragile when disconnected from shared human narratives. Psychological distance, therefore, does not scale linearly with physical distance. It accelerates once certain thresholds are crossed. Loss of real-time communication, loss of visual connection to Earth, loss of returnability, loss of shared time. Each threshold removes another layer of familiarity. Each removal requires adaptation. Importantly, humans are capable of that adaptation. Research from polar stations, submarines, and long-duration missions shows that people can adjust to isolation and confinement. But adjustment is not neutral. It leaves marks. People return changed. In space, those changes would accumulate across years or decades. A person who has lived most of their life beyond Earth would not simply feel far away. They would think differently, value differently, relate differently. This raises a critical point for the broader question of the lifetime travel. Distance is not just something a human crosses, it is something that reshapes them. A lifetime spent far from Earth produces a human who is psychologically distant, even if physically present again. Return does not erase that distance. It persists as a gap in reference, experience, and belonging. This suggests that the true limit of human travel may not be propulsion, biology, or even time. It may be identity. How far can a person go before they are no longer meaningfully connected to the culture that sent them? That does not make the journey invalid. It simply reframes its consequences. Some individuals may welcome that transformation. Others may resist it. Humanity is not uniform in its tolerance for distance, ambiguity, or isolation. What matters is recognizing that psychological distance grows whether we acknowledge it or not. Ignoring it does not make it disappear. Planning for it does not eliminate it either, but it can soften its impact. Space does not rush this process. It allows it to unfold slowly, quietly, over years of motion and waiting. The mind adapts, but it does not remain unchanged, and that adaptation, more than any physical boundary, defines how far a human can truly travel in a lifetime, not just in space, but away from the psychological gravity that once held them in place. Eventually, the question of distance turns back on itself, after planets, stars, speeds, bodies, and lifetimes have all been stretched to their limits. Something quieter remains. It is the realization that travel is not only about where a body goes, but about what a life touches, absorbs, and carries forward. By that measure, humans have already travelled very far, even when they never leave Earth at all. From the moment a person is born, they are embedded in motion that predates them and will continue long after they're gone. The planet moves, the sun moves, the galaxy moves. A human life unfolds inside that motion, carried along without effort or permission. Staying home does not mean staying still, it means participating in a journey that is already underway. This reframing matters because it shifts the emphasis from achievement to relationship. Instead of asking how far a person can go, it asks how far a person can reach, influence, understand, or belong. These distances are not measured in kilometres, they are measured in connection, awareness, and continuity. On Earth, humans routinely travel across immense spans of time without noticing. A conversation can bridge generations. A book can connect minds separated by centuries. Scientific knowledge accumulates across thousands of lives, each one adding a small increment. In this sense, a human who never leaves their hometown may still participate in a journey far longer and wider than any physical voyage. Space travel makes this easier to see because it exaggerates the trade-offs. To go physically far, something else must usually be sacrificed. Time, connection, shared history, bodily comfort. Staying closer preserves these things, but it can feel less dramatic, less heroic. Yet drama is not the same as depth. Consider how much of the universe a human can already access from Earth. Telescopes reveal galaxies billions of light years away. Spectroscopy allows us to know the composition of stars we will never reach. Mathematics lets us model events that occurred before Earth existed. In terms of knowledge, humans have already crossed distances that bodies cannot. This kind of travel does not demand isolation or abandonment. It does not require leaving behind everyone you love. It integrates naturally into a human life. You sleep in your own bed and wake up knowing more about the cosmos than any previous generation. That is not trivial. It is extraordinary. There is also the distance travelled through imagination. Humans routinely inhabit other worlds mentally. Fiction, simulation, visualization, and hypothesis allow the mind to explore scenarios that the body never will. These mental journeys shape values, expectations, and creativity. They influence how societies decide what is worth attempting physically. Imagination is often dismissed as secondary to action, but without it, no action occurs. Every spacecraft begins as a thought experiment. Every mission begins as an idea. In that sense, mental travel always comes first. Staying home also preserves something subtle but essential. Context. Earth provides a stable frame of reference that allows meaning to accumulate. Culture builds on itself. Traditions persist. Relationships deepen. These processes depend on continuity. They are difficult to maintain when people are scattered across extreme distances or desynchronized in time. A civilization that sends many individuals far away risks thinning itself. Knowledge fragments. Shared narratives weaken. Continuity becomes harder to sustain. By contrast, a civilization that stays mostly together, even while exploring observationally, can deepen its understanding without losing coherence. It can travel far intellectually while remaining grounded socially. This is not an argument against physical exploration, it is an argument for balance. There is also the reality that human satisfaction does not scale with distance. Studies of happiness consistently show that novelty provides diminishing returns. New experiences are stimulating at first, but meaning tends to come from mastery, contribution, and relationship. These are not location dependent. A person can feel deeply fulfilled while living a small geographically bounded life. Another can feel empty while crossing continents. Distance alone does not guarantee richness of experience. Space magnifies this truth. The farther one goes, the more stripped down life becomes. Essentials dominate. Luxury disappears. Social circles shrink. Meaning must be generated internally or within a very small group. Some individuals may thrive under those conditions, many would not. So what does it mean to travel far even if we stay home? It means recognizing that distance is not a single axis. There is physical distance, yes, but also cognitive distance, emotional distance, historical distance, and ethical distance. Humans move along all of these axes throughout their lives. A person who expands their understanding, who challenges inherited assumptions, who empathizes across differences, who contributes to knowledge or care, has travelled far in ways that are difficult to quantify, but easy to feel. Space travel often serves as a metaphor for these inner journeys. We project our desire for expansion onto the cosmos because it offers a clean, dramatic canvas. But the underlying impulse is not really about space, it is about growth. This becomes especially clear when considering the cost of extreme travel. Leaving Earth permanently, losing contact with everyone you know. Accepting irreversible separation. These are not purely technical challenges, they are human ones. For most people, the cost would outweigh the benefit, not because they lack courage, but because their values are anchored in connection rather than reach. That does not diminish the importance of those who do choose to go far physically. Their journeys expand what is possible, they test boundaries, they gather information that cannot be obtained otherwise, but they do not define the only meaningful way to travel. There is also an ethical dimension. Humanity's greatest challenges are not spatial, they are relational. Climate change, inequality, conflict, sustainability. These problems require attention, coordination, and long-term thinking. They require staying with the consequences of our actions rather than escaping them. In this context, staying home is not passive. It is a form of commitment. Travelling far while staying home means engaging deeply with the world that exists rather than deferring meaning to distant destinations. It means recognising that Earth is not a starting point to be abandoned, but a complex system to be understood and cared for. This does not preclude exploration. It contextualises it. Another way to think about this is in terms of legacy. A human lifetime is brief no matter how it is spent. What persists is not distance covered, but impact left behind. Teaching, discovery, kindness, and stewardship ripple forward through time in ways that physical travel cannot. A person who contributes to knowledge enables countless others to travel intellectually. A person who builds resilient systems enables future generations to choose their own paths, whether outward or inward. In this sense, staying home can enable others to go far. There is also humility in recognizing limits. The universe is vast and it does not owe us access to all of it. Accepting that some distances are better observed than crossed is not defeat. It is discernment. Human history is full of examples where restraint proved wiser than expansion. Knowing when not to go is as important as knowing how. Space invites a different kind of humility. It shows us that we are small, temporary and fragile. That awareness can either provoke anxiety or foster care. When people look at Earth from space, they often report a shift in perspective, a sense of shared fate. That shift can occur without leaving the planet, it can occur through understanding. So when we return to the original question, how far could humans actually travel through space in a lifetime? The answer is both expansive and constrained. Physically, not very far unless we accept profound trade-offs. Experientially, extraordinarily far, even without leaving home. The deepest journeys humans undertake are often invisible. They involve learning to live well with others, learning to steward complex systems, learning to face uncertainty without fleeing from it. These journeys do not make headlines. They do not produce dramatic images, but they shape the future more reliably than any single leap outward. Space travel remains important. It expands perspective. It tests ingenuity. It satisfies curiosity. But it is not the sole measure of ambition or success. A civilization that understands this can explore without losing itself. It can send probes, ships, and perhaps people outward while keeping its center of gravity intact. In the end, traveling far is not about maximizing distance. It is about expanding the range of what human life can meaningfully engage with. Some will do that by leaving Earth. Many more will do it by staying, learning, teaching, building, and caring. Both paths matter. The universe will continue moving regardless of what we choose. Stars will burn, galaxies will drift, time will pass. Within that vastness, human lives will continue to be brief and precious. What we do with them does not have to involve crossing interstellar voids to be significant. Sometimes, the farthest journey is the one that deepens understanding without leaving familiar ground. Sometimes staying home is not an absence of movement, but a different kind of travel altogether, one that unfolds quietly, steadily, and continuously, without needing a destination to make it meaningful, as the motion of life itself carries on, still open, still ongoing.